Well, first of all, good morning, everyone. It's a nice morning. You all are here. I'm just going to start. Before I start, I want to say a few words. It is a quite tradition to do that, and I also respect that. I would like to begin by acknowledging the traditional owner of the land on which we are meeting and having this workshop today, and pay my respect to all elder past and present. And yeah, that's the start. So why we are here, of course, is a BCI workshop. Well, not quite BCI workshop, but more of a standardization of BCI workshop. What it means is we are gonna talk about how we can create a standardization so that we can connect computational intelligence, which is machine learning community, and the neuroscience community, which is very hardcore and just focus on very basic science, and how we can connect these two, which is a bridge, so that we can create lots of BCI application. And that's all this workshop is trying to teach here today. This workshop is thankfully sponsored by TensorFlow and Aunt Neuro. Aunt Neuro is sitting here. There's a few devices we're gonna demo around the session a couple of times. Can you hear me? Am I audible? Yeah. Okay. It's audible, right?
Maybe just plug in the mic a little bit.
Yeah. That's working. Yeah, that's right. I was just saying that, so this course, this workshop is sponsored by Google TensorFlow. Actually, it's a part of Google TensorFlow Award received last year between me and Sunny Verma, who's also here presenting later on in the workshop. And Aunt Tiro is thankfully also supporting this workshop, bringing devices, and came all the way from Melbourne and Brisbane to support that yesterday. What we're gonna do in the workshop, we will go through a bit of introductory things in the beginning. I'm gonna put this away. Start with more introductory thing with the BCI. I'm not sure, I believe there's a mix of background here with the people. And we go through from there to, I show you, I should open this. So this is sort of outline how we go through the workshop today. There will be lunch in the middle, of course. So we start with this introduction. First one, which is a bit of those who are not aware what BCI is all about. I believe everyone is a part of buzzword last 2 years, thanks to Neuralink and Elon Musk. And followed by a talk from Luigi Bianchi from University of Rome. Unfortunately, time zone is too weird for us and there. That's like a 2 a.m. there, so he can't join. So we have recorded version from him, but he will be available once he wake up for answer any question. So we will have that. He's actually a chair of IEEE Standard Association, where we are creating this standard about standardization. So he have a talk, and followed by, we're gonna do a bit of data collection with Aunt Neuro here, and any of volunteer from you are welcome to do that. I will happy to have your brain data. Then we have a Google TensorFlow expert known as Josh Gordon. He will be joining live. Again, he's in US, so US, Europe, and Australia time zone doesn't really align pretty well. So he will be joining by Zoom. We are also having quite a number of participants on Zoom at this moment. So it's like off and online, but it's more of hands-on workshop. So you are on more advantage. So just want to let you know. Well, then we have a lunch, followed by lunch. We have a bit of case study with Dr. Harvey sitting on the backside. And from there, we put together all these two things together and go through TensorFlow now. So we're gonna converge everything and apply this all knowledge we gain from now to up to lunchtime and do this 2 to 3:30 p.m., which is machine learning using TensorFlow for BCI signal. When I say BCI signal, what we're trying to teach there that how we can apply standardization, how you can use the existing data, and how you can process as well. So kind of connecting these all dots together. Of course, I believe some of you know about TensorFlow, some of you know about BCI, some of you know cognitive neuroscience related stuff. So we try to connect dots there. So that's where we want you to do some hands-on more. So Google TensorFlow is online version called Colab. There will be instruction later on how to use it. You download that notebook, run in your computer, essentially on browser, not in your computer, and you can follow the instruction as we goes and give a try by yourself. So that's the plan for today's workshop. From there, I'll move to next slide to give you a bit of introduction, and I will hand over to my colleague Yancho here to talk further on that. Questions so far? Anything you think is not so sure? Screen is visible on there. Well, so BCI, I mean, it's quite of, like I said, it's a buzzword. It's thanks to Neuralink because it's a quite of celebrity, and if you say something, it becomes quite of media attention. So brain-computer interface, quite common nowadays, but people, although running toward BCI, but they still not so aware about lots of bits and pieces, which is come from neuroscience and psychology. And I'm gonna talk briefly though, but let's see what we can get out of that. So John Wolpa, which is like one of the big figure in brain-computer interface community, well, his definition of BCI is that a way of communication where you don't need peripheral nerve. What that means, if you see these two figures, left and right, the green one and the red one is what more, red one is what more traditional way how we interact. When I say traditional, our human way how we interact. We generate signal on the cortex, on the brain, pass those signal from different part of the process, and then it goes to your muscles, and then you take action, like you're holding this mic I'm doing now. But when we talk about BCI, you can kind of skip all these things, and signal originated in your cortex alone can directly interact with the system or environment or whatever action you want to take. That's the fundamental goal and definition what BCI has come from. And that's pretty much everyone tried to achieve. And that's quite fascinating in sci-fi sort of when you think about it. Some great example, if I pick up from the movies, is if you look at the Matrix, where they hook up with the something on the spinal cord, that's sort of BCI, so that they can project into a sort of virtual world. Similar, so many other similar sci-fi movie is showing this kind of BCI, but of course that's a far, far goal, but that's where we are heading on with the BCI. Yeah, this paper is from 1973, and I think you can call him father of BCI, Vidal. He created one of the first brain-computer interface or communication. When I say 73, it's like a 50 years roughly. And his system is look like this, very huge. This is a setup from his lab, it's UCLA in 1973. And he have like a bunch of computer screen and decoder, encoder, there's no GPU that moment. So computer processing unit are also pretty huge. But he's managed to able to, I mean, this is further down the road, following the same system by Niels Bohr is another famous figure in BCI who created a one fully working version of BCI in 1999. I think he is in Germany, if I'm not wrong, where this patient is able to type or what he say, he is able to write a letter to Professor Barbaumer based on this BCI system. Again, pretty long time ago, right? So it's not new deal, it's just more buzzword, like I said, and more accessible than before ever. Well, BCI, when I talk about it, the essential component is how to measure brain signal. And if that's the major key, and if that brain signal is not measured properly, you can't really do BCI, a brain-computer interface. And there's a lots of utility. These the most common, or I should say, most famous in terms of medical application, ECOG-based BCI, or measuring brain signal using UTHA electrode or array. It's very, very famous, and is there since, again, last 30 years or even more. And then this very latest one from, like, I want to put here because they are very similar. So it's not a new idea again from Neuralink, it's just more density. I just want to say that. And so this N1 sensor, which Neuralink is developing for more consumer market rather than for medical purpose. There's a other non-invasive technique as well. So here you don't need to have an implant, but what you can do is simply read the signal from the scalp, just putting something on the top of your head. For example, what we're going to do with Ant Neuro today, we have EEG system here, but there are MEG and FNIRs. They also good to measure brain signal, but of course, not so great in terms of fast BCI or real-time BCI, because they're huge system, of course, not that feasible. And that's where I want to talk more. So all these systems have one or other trade-off advantage, and depend on what required, people can, of course, switch between them, what they want to use. So when we talk about BCI specifically, brain-computer interface, we hope to see something in real time, like we move hand, we want the action happen, right? That means it should be fast enough. In that case, it's supposed to have a high temporal resolution, which represent the time. And same time, if it's portable and non-invasive, that's even great. And that's where the best fit is EEG device so far. There's another device like FNIRs, which is getting there, but still slower system for BCI devices. Why we want to do BCI? Of course, there's a multiple motivation. And I think that as always, any wearable devices, whatever we have now, wristband or EEG or FNIR, medical application is always one of the motivation to help people who have some sort of stroke or spinal cord injury, so that they can communicate. That's where the BCI come from. And from there to pretty much everywhere. For instance, I call it from disability in terms of lock-in syndrome to a healthy people for entertainment and playing games and stuff like that. And maybe everyday life in coming years, I don't know, with Neuralink, thanks to again them. This is one of the example I did, or I should say my lab did a while ago. This is a BCI-based control game. It just contained few BCI components. I just want to show this one. Let's see if I can play it. It's very nice Candy Crush game actually, but you can use different kind of brain signal to play this. This happened like a few years ago, and the goal is not to create BCI in this specific video, but goal to understand BCI, how BCI actually works. Understand BCI is a skill. Can you acquire this a skill? Can you improve this skill? Because there's already, like I said, it's 1973, 1999, so it's happening since last 50 to 60 years. And really not much change so far, except the algorithm and fancy GPU systems. They're still working same. So here, user is playing the game using mouse, right? And then you see mouse change slightly to, I don't know what it says. It's changed to attention, for instance. And now user has to pay a lot of attention to charge this gun, I guess. And based on this charging gun, it can kill this monster, which is a part of the game. There's a one BCI component. You will see a couple of more in this video. And we use Candy Crush just because it's a bit more addictive game. People can continue able to play without get bored, without get frustrated at the same time. That's why it still is quite popular game, I guess. Now, you see another BCI component where, yeah, it's called motor imagery, where they have to think left and right. And this TNT, which is essentially a bomb, will drop on one of these player, either player or monster. A very nice, simple example. Again, this is based on EEG, for instance. This is another BCI. Okay, this is again repeated for attention, but there's a few more BCI component within embedded in this game to understand how BCI actually works. So what I want to show with this video that this is not, although quite a buzzword in last couple of years, but things are happening from a while on this. My personal definition for BCI, I like to call it, BCI is something which is more about how you can replace, restore, and enhance your capability in terms of communication as well as enhancing cognition. When I say enhancing cognition, it's more of like creating resilience, creating adaptive atmosphere based on the BCI, replacement, where you are able to have control. For example, people with lock-in syndrome, they have able to control the things around them, and restore to help them to acquire this ability using, let's say in this case, robotic control with the brain. So that's another way. There will be some videos later on to see how it works as well. This is another application also from the lab. I just want to place a very quick one. Okay, this is the YouTube. So here again, BCI has been used to make the drone fly using motor imagery essentially, right? If I'm not wrong. Let me skip this few stuff. So you see user is wearing a wireless headset. So like a standard headphone, very similar to that. And they are able to control this drone using different kind of brain signal. And here is motor imagery actually. Not sure why there are two drones there though. They're gonna hate each other. Okay. So this happened in the lab again, here in UTS, in Tech Lab, we call it MPMR, motion platform and mixed reality lab. This is the work from, there will be talk later on with Dr. Harvey. So some of his students did this a couple of years ago, again, using the headset. So move on from there. This gives you a pretty good idea how BCI work, and it's already working with quite of these fun, entertaining thing. Well, there could be several different versions of BCI, of course, and my personal one is passive BCI, which I'm always very interested in, because then you don't need to actively interact with the things, but signal coming from your brain do things for you, and you may be not aware, and maybe things adapt for you. But there are, of course, active and reactive as well. Active and reactive, which is more stimuli driven and more active interaction. Active is very much like what you see in the drone, where users actively interacting to control the drone, and reactive when you see something and some signal evoked in your brain. That's a more reactive. So you essentially can show something in the screen, which we're gonna do later on, and it creates some signal and captured from the brain and can be used for controlling. And today workshop also we're gonna focus on reactive BCI, which is a bit easier in given the short duration of the workshop itself. So we're gonna do what we call, okay, before we go there, we're gonna do P300, which is a kind of signal explained by Yancho in next slide, and another is called SSVP, which is another flickering based signal. So both are a bit of flash based signals. So if anyone have any problem, please let us know now. I don't want anyone to have some sort of epileptic stroke or something. So Yancho, hand over to you.
So hi, I'm gonna talk more about the reactive BCI, like the brain signals we're gonna use for today's workshop is, like Avinash mentioned, there are gonna be some flickering in the following slides. So make sure you're comfortable with that. So the reactive BCI here today we're gonna talk about is a visual evoke potential that's including the P300 and SSVP as well. So the visual evoke potential is like the brain signals that we recorded from the occipital, or we call visual cortex of the brain, when we process the visual stimulus. And different visual stimulus can cause or induce different potentials as well. So for example, this one, we call it transient potentials. For example, like P300, it is induced by the low rate of stimulus and happened what we have here on the right side of the amplitude after the stimulus onset. And another one is steady state, which is induced by the high rate of stimulus. And we call it, for example, SSVP here. So first we start with the P300. So P300 is like one of the most like common or most used event-related potentials in EEG signals. So it is induced by the infrequent stimulus. For example, the like most popular of the audible task, and will result in higher amplitude signals around 300 milliseconds after the stimulus onset. And the stimulus type could be like visual, auditory, or tactical. Here is an like very easy and simple example of the visual audible task that induce P300. And you guys can give a try to just follow the instructions in the video. And it's quite easy, just respond to the target. The target is the right stimulus, yeah, and just ignore the rest of them. How the video is not working, but it's okay. Just so this video is just mainly to like have you guys have an idea of how the P3 is induced, but it's not working, but it's okay. So another application that we used, like P300 based application, is we like trying to help for example, disabled people to like then use the brain activity to spell the word, which is also P300 based. Let me see if I can. So for example, in this video, this group gonna use the brain activity. Just ask the participant to focus on the screen, which is a virtual keyboard, to spell the word like free, FREE, one by one. Yeah, and as you can see, sometimes it causes some typos as well. So of course, here are some like advantages and disadvantages for P300 BCI as well. So the good points could be it's definitely a great tool for assessing the cognitive functions like attention or the speed of stimulus processing or the error awareness. And also it does have the high accuracy using short training time, which makes it more effective. And also the classifier offers like faster response as well. And also the cons comes to it shows the low information transfer rate. And also, as you can be aware of, especially for the visual P300, it does need a monitor or other external equipment to generate the simulation or the stimulus. And the next is the steady state visual evolved potentials, which we call, or we see the SSVP here. So it's mainly induced by the high rate or high frequency of this visual stimulus. And also could be like replaced by the auditory, gonna be the steady state auditory evolved potentials. So this is the visual based. So we also gonna focus on the visual based here today in our workshop as well. So this is an example of the SSVEP-based assistance system that Dr. Avinash has been done for the past few years. The aim is we want to use the SSVEP-based BCI system to control the robot arm to do some actions. As we can see, there are several flickers on the screen. So all we need to do, or the participant needs to focus one of them and to send the actions or the orders to the robot arm to do the actions. So that will be and either pick up the different food or the drinks. So different flickers represent or indicate different actions. So as we can see, the advantages are quite obvious. So it does not require any training and also have the higher information transfer rate and also the higher ISNR compared to the other EEG signals. And also have some limitations to, for example, the certain frequencies of the flickers and also like highly depend on the flickering itself and also gonna cause some uncomfortableness in the long using. So that is the general introduction for the BCI and also P300 and SSVEP for today's workshop. Yeah, and again, back to Avinash. Thanks for listening.
To ask question, but we can continue and you can interrupt anytime and we can talk later today around end of the workshop. We can talk more, discuss also in the lunchtime. So I will just continue going. Like I say, you can feel free to ask. Next one.
Can I ask a quick question?
Yes, please.
So in those examples, sense that once there's a decision about execution, that's it. The system goes all.
Fortunately, not at this moment. Yeah. So you take action. If it's mistaken, then it's just mistake. I'm gonna go ahead for now. I mean, those are the nice example where we just try to make it work, I would say. But yeah, this is actually a very interesting point. So far, I don't know so much system where people also talk about you control and then you stop. There's a system where you talk about intention and actual action. There's some work happened there, but not too much about once you issue a command, a kill command, and then you just go ahead and does the job for you. So that's actually an interesting point, and you should consider it, I guess.
I think it's
Yeah.
from a neuroscience perspective. Utility.
That's right.
So we already know what we're looking for, so we just have to put them together.
And that's where my area comes in as well, where error potential, or I call it passive BCI, where we do this thing on the backside of the brain without. So you issue a command, but you think, okay, it's a mistake. We also have some signal from the brain. It can be connect back to those BCI to kind of able to stop, but we never try that. It's a good point to play around with that. Well, now you are in this workshop, it's also important to go through it, why we even doing this workshop a bit more in detail. And like I said, so Luigi Bianchi, who's from University of Rome, he has a recorded video and unfortunately can't be live. He really want to be, but he can't. Okay, we also have one question here. I'm gonna answer later on the chat on the Zoom. But I'm gonna play the video meanwhile, so we have stick with the time. So I'm just gonna play, and like I said, feel free to ask question and interrupt anytime. Sorry, I'm resharing because somehow it did not sound. 1 minute back. Sorry for torturing that to you.
Communication system that does not depend on the brain normal output pathways of peripheral nerves and muscles. Current BCIs make use of EEG activity recorded at the scalp or single unit activity recorded from within the cortex to control cursor movement, select letters or icons, or operate a neuroprosthesis. Finally, the central element in each BCI is a translation algorithm that converts electrophysiological input from the user into an output that can be used to control external devices. The main objectives of brain-computer interfaces can be categorized into 5 different applications, which are replace, restore, enhance, supplement, and improve the natural CNS outputs. And this is achieved by modifying the interaction of the central nervous systems with either the rest of the body or the external world and environment. Regarding BCI application, they have been proposed for in the field of communication, device control, neuroprosthetics, rehabilitation, and also in non-clinical areas such as gaming, monitoring, and group decision-making through collaborative BCI. In this figure, you can see a very old system in which there is an analog EEG amplifier which collects brain signals through electrodes. Signals are then conveyed to an AD card which is installed on a PC. And then signals are processed in order to allow an interaction with the environment. So there are some applications through which one can communicate or control the room or the environment. Feedback is then provided to the user via the same application or through a dedicated PC monitor. Regarding the nature of the acquired signals, brain activity is usually recorded from the scalp by means of EEG or magnetoencephalography, or by means of electrocorticography, or by means of intracortical recordings, but also metabolic methods such as fMRI and near-infrared spectroscopy and others also are used. It is time for some examples. Let's start with the work made by Yusun Chik about 15 years ago, in which he used fMRI to allow people to navigate into a maze, a labyrinth, by analyzing mental tasks, so brain signals. In particular, he asked people to perform 4 different mental tasks, which were a mental calculation, a mental speech generation, and the right hand and left hand motor imagery. Then he acquired brain signals by means of fMRI and identified activation patterns which were specific and categorized each of the 4 different mental tasks. Because the user will have to control the movement of a cursor which is into the labyrinth, to each of the 4 tasks a movement direction is bound. Then the user was put in front of the maze, a cursor appears, and so the user has to move the yellow cursor from start to the right. And to do this, he had to imagine to move the right hand. Then brain activity was acquired and computed activation pattern and compared with previous 4 activation patterns that were acquired during the calibration phase. A correlation index was computed. You can see the bar, and the highest bar, which means the highest correlation, is the blue one, and so the cursor was moved to the right. Here in this slide, you can see the most widely used and described EEG-based BCIs with different paradigms, so the P300, the sensory motor rhythm, the steady-state visual evoked potential, and slow cortical potential, even if this last is no longer used. As a second example of a BCI, I will talk to you about steady-state evoked potentials, which occurs when pulses of stimuli are provided to the user, which can be visual or acoustics or somatosensory. In this case, they are visual. Imagine a flickering light which flickers at 15 hertz. And what happens is that if a user is watching this flickering light, the EEG signals get synchronized with the stimuli. Spectral analysis then reveals peaks at 15 hertz and its harmonics. How can this be used to drive a BCI? Imagine to have two flickering lights flickering at 7 and 9 hertz. If a user is gazing at the 7 hertz flickering lights, by analyzing its pattern, you can find peaks at 7, 14, 21, 28 hertz. On the other side, if a user is gazing at the 9 Hz flickering lights, you can find peaks in its spectrum occurring at 9 Hz, 18 Hz, 27, 36 Hz, and so on. So by simply analyzing real-time brain signals, it is possible to deduce which flickering light the user is gazing at, and it is possible to bind a different meaning to each of the light as if they were switches. You can use virtually an unlimited number of flickering lights, up to 40, I think, has been described in the literature. Another widely used BCI paradigm is based on the P300 component, which is an event-related potential, which is elicited in the process of decision-making. It is thought to reflect the processes which are involved in the evaluation and categorization of certain stimuli, and for this reason it is usually elicited by using the so-called audible paradigm, in which there are two categories of stimuli: the target, which occurs with low probability, and the non-target or standard, which occurs more frequently. They are mixed together, and the evoked responses are different. In this figure, you can see the responses relative to 16 different sensors. In orange, you can see the responses to the target stimuli, and in blue, the responses to standard stimuli. Green bubbles represent somehow a measure of statistical significance in a t-test on a sample-by-sample base. How can this be used in BCI? This has been used in the famous P300 speller application, which letters from the English alphabet and numbers are disposed on a 6x6 matrix. A user is asked to watch a letter that he wants to communicate, for example, the P letter, and then rows and columns start to flash in pseudo-random order. So there are 12 different stimuli, 6 rows and 6 columns. 2 of them are the target, which correspond to the row and the column which contains the P letter, the other one being representing the standard stimuli. You can see a complete set of stimuli, of 12 stimuli. 2 of them contains target stimuli. A complete set of 12 stimuli is called an iteration, and usually more iterations are needed in order to increase the signals to noise ratio, which is quite low in this class of application. In this figure, it is repeated 8 times, so 96 flashes are needed. Then all evoked responses are analyzed. There are 12 different stimuli, and it is computed the response after the flashing of the first row, of the second row, the third row, and so on. And you can see that the evoked response after the third row stimulation is different with respect to the other, which suggests that the letter is on the third row. If you repeat the same procedure for the columns, relatively to the column, you can immediately identify the fourth column and the P letter at its intersection. We have seen 3 different examples with different paradigms and different acquired brain signals, but all of them share the same functional model. There is a user, some brain signals are acquired, then they are preprocessed, some features are extracted, and then there is a classifier that outputs a label, usually. Then there is an application interface which drives directly the application, which then provides the feedback to the user. What it is important here is that in general the classifier output is a logical symbol, a label, which in general has no semantic meaning. This meaning is provided by the application interface, which encodes sequences of logical symbols such as the third row and the fourth column to generate a semantic meaning to the selection. In this case, the typing of the P letter of the English alphabet. It is clear that BCI is a highly multidisciplinary research field in which several experts such as psychologists, engineers, neurologists, neuroscientists work together, and so there is a huge amount of experts with very different backgrounds. This may represent a problem because there are different experts, different visions on the same maybe paradigm and BCI implementations, different objectives for the use of BCI, different languages, different methods, and so on. Researchers may also be interested in different aspects of BCI, such as classifiers as compared to preprocessing techniques or signal acquisition or feature extraction. Also, the description of BCI can vary according to the, for example, cortical area recorded, to description of the input signal, extracted features, feedback modality, application, and so on. And these also reflect the background of the researcher. This is a highly multidisciplinary research field in which a huge amount of researchers with different backgrounds work together. So to avoid confusion, we need standards, because too much time is spent to synchronize the terminology among different experts. For example, even performance may have different meanings depending on the vision, on the goal, on the objectives of the researcher. Too often it is impossible to compare systems. Then too much time is spent to try to reproduce or adapt tools and methods. Too much time is spent to share resources, for example, because of the lack of standard file formats. And then it is virtually impossible to allow a certain degree of interoperability among existing systems that already are available. Finally, it is hard for a user to realize which BCI is more suitable for his needs. And of course, all of these dramatically limit progress in BCI. So about 4 years ago, after having met Carol Carey, which represented the IEEE Standard Association during a BCI Society meeting, she instructed me about making a proposal for a standard BCI. I made a request. The code name is P2731. The title is Standard for a Unified Terminology for Brain-Computer Interfaces. It's totally free. You can join the working group. It is sufficient to send an email at my email address. Carol Carey is the vice chair of this working group, and Pradeep Balachandran is the secretary. In our working group, we have some guidelines that are that standards must provide clear advantages to the entire community, including the patients, caregivers, scientists, in terms of efficiency, quality, and safety. Then standards must be minimally invasive with already existing systems, because there are a huge amount of BCI, fully working BCI system worldwide, and people, of course, does not want to change the way in which they are working just to be standard compliant. Then they should not reinvent the wheel, but if it is possible, make use of already available standards. They must be easy to understand to all stakeholders. And finally, which is really important, they should not represent a limitation to the implementation of new paradigms or represent in any case an obstacle to the innovation. In our working group, we have identified three main activities, which are the creation of a BCI glossary, then the creation of a unique functional model which could cover the vast majority of BCIs, and then finally the data storage, which means what should be stored into files and why. We are actually not really interested at this stage to define how to store, that is, which means the file format, because for this we want also to involve manufacturers and all stakeholders. Regarding the BCI glossary, we have actually realized a glossary formed by more than 300 of terms. Each term comes with a definition, with some references, with indicates the source from which the definitions are taken. The first draft of the glossary has been published last year on BCI Journal, but since then it has been improved a lot. Okay, let's start now with the functional model, which is quite empty now. We will fill it with several elements during the next minutes and slides. So there are essentially four different elements. The user, which is the most important one. Then there is the transducer, which is a module which is responsible of the signal acquisition and preparation, and also signal processing. Also the classifier eventually is included into the transducer. Then we have seen that there are several different paradigms that can be used, and so there is a very small module here, which is responsible mostly of synchronize all the other modules in order to deliver the proper information and timing to all the BCI system. And finally, there is the control interface, which is responsible of collecting and analyzing and processing the output of the transducer, usually a classifier, so some labels, and then convert them into action and interaction with the towards the external environment. So let's start to fill this very empty functional model, starting from the user. We have brain signals. You can see here the brain state of the signals affect the physiology of the signal. We want to acquire physiological signals from a brain, from a subject, such as signals such as the P300 amplitude, response latency, and or CD state, evoked potential frequency, mu rhythm, and things like this. The physiological signals that we want to acquire, however, are influenced, affected, and modulated by the psychological state of the user, because motivation, eventually depression, or skill, abilities, or frustration from a user can affect the amplitude and the patterns that we want to analyze, brain patterns that we want to analyze. Physiological signals are also affected by other signals, such as muscular activity. We have seen that eye movement can be used to modulate the amplitude of the peak in the spectrum of EEG signals in steady state visual evoked potential, but there are also involuntary muscles, and all these signals are somehow acquired. So we want to acquire physiological signals from the brain. We actually collect also other signals, not just brain signals, but also other signals. We collect also some noise, which is collected from the environment, such as the power line noise and things like this. These physiological signals from the brain or from the muscles or from other parts of the body can be acquired, well, should be acquired. So there is the signal acquisition and preparation module, which is responsible of acquiring and prepare signals coming from the brain through different recording techniques, EEG, functional magnetic resonance imaging, and so on. And also other signals can be acquired, such as muscular activity, electrooculogram, and other signals. These data are then transferred to a signal processing stage, which is responsible of initial processing and pre-processing, for example, for artifact removal, for spectral space, and time domain filtering, such as low pass filter, notch filters, but also independent component analysis, Laplacians, and things like this, and other preprocessing methods. Then pre-processed signals are conveyed to the feature extraction module, which is responsible of extracting relevant elements from brain signals, because not all brain signals are conveying useful information, so we have to remove useless information from the brain to try to increase the signal to noise ratio, for example. And the extracted features can be forwarded to the classifier or maybe to a regressor. Classifier, as in the case of the P300, or a simple classifying in the case of the fMRI that we have seen. And then the output is usually a label, the label which is produced and generated by a classifier, such as the third row, the fourth column in the P300 speller, and so on. Then we have the model responsible of the handling the protocol paradigm, so trial handling, generation of stimuli, such as in P300, or maybe not if the paradigm does not needs them, and in general timing clock. The output of the classifier then is forwarded to the control interface in which there is the encoder, which creates a map of sequences of logical symbols and maps them into semantic symbols. For example, the third row and the fourth column in the P300 spell are mapped to the P letter in the English alphabet. Then the encoder interacts somehow with the feedback, with the application, with the stimulation, and etc. But there can be also an agent which tries to boost the performances of a system by implementing, for example, some prediction strategies, such as for predicting the words that one wants to spell in order to communicate, or maybe there can be sensors that try to avoid obstacles when the application is implemented for driving a wheelchair. So if there are some stairs in a room, there can be sensors which automatically try to avoid accident of this kind. And then from the control interface, there is the interaction with the environment. So, for example, the selection of a letter or some other things which depends on the application. This is the final functional model, the final at this stage, because it is a work in progress. So we can change, we can modify it. If you have any ideas regarding how to improve it, it will be really, really important for our working group activity. So if you join our working group, you can participate. But also, if you don't join the working group, you can analyze, stress this functional model and please tell us where it fails, if it fails, or how it can be improved. This quite complex functional model is important because once one has realized what are all the elements, it can be really useful to describe BCIs according to the different visions of different experts which deals with BCIs. Or stakeholder. For example, the point of view of a user in terms of performances is to try to maximize the number of interactions that the user can have per minute, for example. And this can be evaluated here at the output of the control interface. But experts in machine learning are more interested in analyzing what is the accuracy of a classifier. So evaluate the performance of a system here at this point, at the output of the classifiers. Because if there is some prediction strategies which is implemented, this may affect the overall performances of a system, but experts of machine learning are not interested in this. Maybe there are computer scientists which can be interested in this model. Maybe there are other experts which are more interested in developing something here. Clinicians, which are, for example, involved in rehabilitation procedures, may be interested in see how brain patterns changes over time during a rehabilitation process. So maybe they want to evaluate and analyze the signals here. So you can see that there are different way in which one wants to evaluate the system because there are different experts in BCI. This is nice for several aspects because with so many experts involved in BCI, there is a lot, there are several things that can be learned, but this complicates things when one wants to share the data and resources. So this is the last part of the presentation, which deals with the data storage. There are on the web a huge amount of freely available data sets related to BCI, but all of them are in different, virtually all of them in different file formats, and a lot of information is missing or can be accessed just on from PDF files, so one has to read the documents and nothing can be actually automated. So datasets must have signals, stimuli, of course, including timing, the classes of the stimuli if present, the sensors information, the labels, the locations, the reference and the ground. This seems to be quite obvious, but in some of the datasets, some of this information are actually missing. The words to be spelled, for example, in speller, or the task to be executed, the encodings, the events needed to indicate rejected epochs, and many other details. In particular, there is a very important difference between what's needed to allow the training, so what's needed to be known before the training, such as eventually some pre-processing which has been applied, filtering, artifact removal, or things like this, filtering either in the time or in the spatial domain. And after the training, what's needed is, of course, pre-processing, filtering, artifact removal, but also information related to classifiers, such as weights for linear classifier, for example, some parameters, and eventually also benchmark. If we refer to the functional model, we can put different colors in different to the different elements. Because we think that we need three different levels of file formats. That is level 0 if for just describing brain signals acquisition. So acquisition parameters, you can see here, and some pre-processing information, some information related to the paradigm, to the stimulation, and some information from relative to the user. Then there is level 1, which is for training a BCI, and it is in red. You can see that there are additional information related to the paradigm, but also some information related to the encoders and eventually to the agent for prediction of some events. And then there is a level 2, which are all the information which are necessarily to provide the feedback. So information related to classifiers, eventually regressors, and a few other things. Now, to prove our ideas and to show what are the advantages of having a unique file format with all the necessary information stored into it, we started to realize a huge P300 database by collecting several P300 datasets from the web. We converted them into a unique data format. We selected then just P300 speller datasets. And then we wanted to implement some simple tools to show the benefit of having a unique file format, just to show how easy it is to extract features from a huge amount of data, to convert the features in ASCII, MATLAB, Weka file formats. It is how easy it is to compare different data sets, etc., and several other tools. And then we want to share our findings with within the BCI community. But the question that I am making to you is, what would you like to do with data sets that you cannot do it now? So please answer this question. So these are the P300 speller datasets that we have collected. You can see on the first column the name of the datasets, the ARC Impact, BCI Competition 2 and 3, some datasets from the BNCA repository, from the IEEE data port, and other from, this is from my lab, and this is from the lab from Wolpov Laboratory in Albany. The number of subject, of character, of stimuli, you can see that we collected more than 1 million of stimuli and different number of sensors, but all of them shared the same 8 sensors. So there are 8 sensors which have been collected in all of these data sets. Different interstimular intervals. Some of them have been pre-processed, some of them have been segmented, but this is not a big, maybe not a big issue. However, we converted all these data sets. It took about 3 months for converting of all of these data sets, which is a huge, really a huge amount of data sets. Keep in mind that one single subject can come with a huge amount of files. So the number of stimuli and the files is really, really huge. All of them have been converted, more than 3 months to convert them in the same file format. A couple of hours to extract the features from all of them and convert them in ASCII or WCAG file format. And to show you how easy it is to extract the features and give the features to people from machine learning, computational intelligence community, this is a tool that I have released in which, if it starts, maybe, yes, it is starting. You just have to load the file. You select a predefined, for example, sensor list of sensors that you want to use. If you want to, you can change the decimation, the encoder, but with another click, you can export the data in ASCII format, for example, and that's it. Or you can do the same thing and export the data in ARF file format, which is the file format used by WCAG. And this is what it is asked from the people from the computational intelligence that works with me, that just wants to have the data. So just a couple of clicks, and they can get access to 1 million of stimuli. So a huge amount of data to play with machine learning. So in conclusion, how to bridge the gap between computational intelligence and neuroscience in brain-computer interfaces? The easy answer is join our working group. It's simple and free. You can send an email to me, luigi.bianchi at IEEE.org. There are monthly web meetings. The next one will be in the end of, I think the last day of June should be scheduled. And it represents a great opportunity to work with other people and to contribute to BCI and its diffusion. We've also published several papers among our working group. That's it. So this is all. Thank you again for this great opportunity. I hope to meet you somewhere in the world very soon. And if you want to contact me, you know my email address, you have my coordinates, you can ask Professor Singh. And more importantly, if you want to join the IEEE 2731 working group, you are, of course, more than welcome. Bye from Rome. Ciao.
Um, So there's quite of information, of course, within a short duration. So try to put all those standard, and maybe you get some idea for sure. That's the purpose, not everything. And like I said, there's a working group called P2731 from IEEE standard, which supposed to be submit a report. I'm also part of that group, working group member. We're creating these standards. And like Luigi mentioned, there's 3 different levels. There's a functional model, there's a data standard, and there's one more, I forgot. How to save the data, a file format. But we are, like I said, we are not interested in how to implement that. It could be any file format, doesn't matter, as long as we have this standard and everyone follow it. And today in the workshop, we will focusing on not functional model because it's much more complicated, of course. The goal of this workshop, I want to remind again that I want to deliver this message that this is really a very critical problem, given keep generating data on neuroscience point, but machine learning, they can access the data, of course, but they need to go through a crash course of cognitive neuroscience before they can understand the data, read the paper, and then make some meaningful sense out of the data so that they can put in machine learning. What we want to do, we want to create some sort of bridge here so that neuroscience data can directly go to the machine learning without putting that much effort. And of course, learning is always good, but at least to get started, no need to go through that much painful process. And maybe that's the reason why BCI, since last 50 years to now, there's no significant change. Things are happening, it's a buzzword, but still the same P300, same SSVP. And the question like asked by Ami here, these are still open questions. People are trying, it's fancy. When you try, it's nice, controlling brain. People love to do that, but after a while, it just go away because it doesn't sustain. And reason is machine learning is not improving it enough so far because there's not enough people doing that. With that, I want to move to next part of the session. Okay, there's quite a question. Anyone taking care of that, I guess? Yancho or Leja, do you see? Feel free to respond the question. And next part. So I mentioned around 12, we will start with the Google TensorFlow crash course with Josh Gordon from Google itself, from USA. And before that to now, we're gonna go for collecting some of the data set, which we're gonna use for remaining part of the session for different things. So any volunteer? Lex, do you want to quickly explain what you gonna happen in data collection? So those are online. I'm sorry you are not here. And that's the advantage. Yeah, please come down here. That's the advantage of being on in person.
I can try and put it up on the monitor.
That's fine.
Anybody else want to get the brand? It's a bit of salty water. Come down, come down. We got three systems.
Share the screen.
Slides into me.
Switch the camera to that corner.
So we're going to cover the 2 experiments we're going to do. So firstly, we're going to do P300, and then secondly, we're going to do SSVP. So for the P300 experiment, you can see it's generally going to be a target non-target experiment. So the target character is going to be A, and then the other non-target characters are going to be selected randomly from B to Z. we're going to show the participant a string of 10 pseudo-random because we replace one with the target. Trial duration 200 milliseconds and trial per block 10. So this is the general information. So hopefully what we'll see is whenever they see the target, they'll go, that's the target, and we'll see an amplified peak at P3. And then hopefully we'll be able to see that in the data, which we'll try and get up on screen, I think. Then after the P3, we're going to be doing SSVEP. I don't have flashing images here, but we've got 2 mini experiments for SSVEP. We have labeled single square data. So the square in the single square is going to flash various frequencies. And when this happens, what we do is in the EEG data, we send an event so that it logs at a certain timestamp what the frequency is. So generally, we're marking in the data when something starts, and that's sort of the idea of the framework is how do we mark this stuff for the machine learning side of things? Because obviously, people working in EEG, they understand markers, they understand, okay, the marker is normally the start of the trial. How do you know when the end of the trial is? Unless you know the length of the trial, you don't necessarily know if it's the duration. Is there a gap between the 2 trials? These are the sort of things that hopefully the metadata are, or the data about the data, will help for the machine learning side of things. So that's the single square. The second square, the unlabeled double square, is because in SSVP, we can see a peak at the frequency that the square flashes at. We've got 2 squares. One is going to flash at 20 Hertz. One is going to flash at 15 Hertz. We're going to just send a marker saying 20 plus 15. We're not going to know which square the participant is looking at. And so hopefully from that data, we can look and see whether the peak is at 15 or 20. We can then tell what the participant is looking at. And then from there, if we had a closed loop system, we could then react based on what the participant is looking at. So I'm presuming we want to demo these. This one. Yeah, I can. So my thoughts were we've got the camera showing, right? So we tilt the camera to the screen and then. We're just going to get the experiment up on the laptop, and then hopefully we're going to try and tilt the Zoom camera up to the screen so that people on Zoom are able to see the experiment as well. So as we can see, Unity is booting up. We just put together the 2 basic experiments in Unity. So there's a plugin for Unity called LSL for Unity. So lab streaming layer is a way of making sure that everything is synchronized. So if we have recording equipment over there recording the EEG data, we've got this computer running the experiment and sending the markers. Perhaps we're writing the events or the trials to a JSON log. Again, going back to the standardization of all of the different data standards and data formats. LSL lets us combine all of those into one neat file. So I'll just give a quick example of all of the three on the screen. So we'll start with the P3. Same warning Avinash and Yanshu gave during the presentation. There will be rapidly flashing images and changes. So if anybody has any sort of photosensitive epilepsy or other similar things, please be aware that there will be flashing images. So as an example in the P3, I believe on here, this version is 600 milliseconds for the letters. We'll find out very shortly. But so for this one, if everybody wants to follow along and play, the target letter is A, and we're going to show a string of 10 digits. So when you just look out for the letter A, that's all you need to do. And so whenever you see the letter A, that's the target letter. P3 in the brain has an increased amplitude, and from there, we can hopefully pick that up. One more time, and then looking out for the letter A. So that's an example of the P3. Whenever we're recording the data, we're going to have everybody hopefully do a lot more than 2 blocks. But that's an example of a very simple P3. You've got other ones oddball where every letter would be the same, apart from one, which would be the target. So say a string of W's and then a V. Or you just have the string of random ones and then the target letter. The labeled SSVP is this square. So again, warning, the square is going to flash quite fast. So every time it changes frequency, it'll send a marker which the recording data will be able to pick up. So I believe the screen is 60 Hertz. So generally we try and align it with the screen so that the flickering matches what the screen can actually do. So it'll go 160, 230, 320, 415, so forth, so on and so forth. So this is about a minute, I think. So we'll just start this. And if you just watch the square, whenever it flashes, your brain synchronizes at the same frequency, and we can see that and the harmonics of the frequency in the brain.
Screen sharing so that I can see the video in full.
Yep. Don't know where it is either. It's sharing.
Now should be there. No, it's still showing.
Yeah, I don't know. Beyond that one, we're sharing. Do you want me to change it back to that one?
I'll still use text.
Yes.
You can change that.
Yes. So looking at the square, there are a couple of interesting questions which hopefully somebody might have thought of is, we know what frequency the square is flashing at. So in the data, we've sent a marker saying the square is flashing at 30 Hertz. In the data at the moment, there's nothing saying how long the square flashes for. So did it flash for 3 seconds and then there was a 2-second rest? Or did it flash for 5 seconds and there was no rest between them whatsoever? These are the sort of things that you don't necessarily know unless the data about the data is included along with it. So potentially at the start of the experiment, you send a big data dump of all of the files, the screen hurts, what everything's flashing at. An interesting one for SSVP is whenever you're analyzing the data, you can pick up interference from the mains power. So for example, in Australia, the frequency of the mains power is 50 hertz. In the US, it's 60. If the screen is flashing at 60 hertz, and an American person in America is analyzing the data and expects to see the power at 60 hertz, how do they know that you're actually seeing SSVP at 60, or are you seeing mains interference? You could potentially pre-process the data and remove the mains frequency, but then you have to note that you've done it. And if you've pre-processed it, you remove the interference at 50 hertz. And then they look at it and they go, okay, I'm expecting to see, you know, a spike at 60 from the interference. If you've not told them that you've pre-processed the data, now they're going to think your peak at 60 is mains interference and they're going to remove that. So potentially these are all the things that actually having the information about the data, not just the data itself, will hopefully fix. So for the final one, it's the dual task or the dual square. So the square on the left is going to flash at 20 hertz. The square at the right is going to flash at 15. And if we had everybody here wearing an EEG cap, hopefully if everything worked perfectly, if you just picked a square at random, left or right, whichever one you want, we'd be able to tell you which one you're looking at by where we see the peaks. So just running through this, it's only 5 seconds. So again, warning for the flashing squares. 3, 2, 1. And once more. So depending on which one you focus on, we can tell you and say if we, if, for example, in the slide somebody had locked-in syndrome, they aren't able to answer. Depending on which square they're looking at, this could be a binary yes, no. So we ask them a question, yes, no. And then we can use this to answer. But obviously, again, what are the frequencies? Is it the left or the right? What's the distance between the squares? Is there any interference? How big are the squares? How many squares are there? Where are they on the screen? This is all information that if we just gave them the raw EEG file isn't necessarily included. And all of these things could potentially interfere. If we have the squares too close together, you get, I believe, the middle point between the two. So if we have 15 and 20, we would see a spike at 17.5 if they were looking at both at once. And so you ought to have harmonics. Sorry, is the amp? Yeah, so if you're looking at both, or one is in the corner of your vision in this case, you'll see a lesser peak at 15, but a higher peak at 20 if you're looking at the 21. So the point of the one square in this one is just to go through the different frequencies and see if we can pick them all up. So it's just an example of, yeah, almost like a baseline. If you just had them look constantly, if you did 100 trials on 20 hertz, then you've got labeled data of one square, so that if you then have potentially unlabeled data, you can pass in the dual task and you can go, okay, we see a peak at 20 hertz that looks, you know, similar to the labeled 20 hertz data. We can go off of that. So I think, hopefully, I was going to say, how is the data setup going? Are we?
Yes.
Yeah, tell me if this works. It should be switching to wireless now. Matteo, Kaylee, do you want? We can do it. Yep. Do you want a microphone?
Now you're going to see a lot of slides.
Do you want a microphone, Matteo, or do you want the lectern mic?
This is
Sorry.
Want to introduce yourself?
Yeah. Hello, everybody. My name is Matteo, and I am from A&T Neuro. As most of you here, we have from different background. My background is in electrophysiology. And just wanted to show you how EEG works and what we're looking at here. So the one that what's your name?
Meow.
The cup that Meow has is an EEG cup. In particular, this cup uses saline technology, in which we just put this cup inside a saline solution, and there are electrodes that pick up the signal through the scalp. So each of these electrodes is composed by a sponge that gets imbued with saline water and then create a connection between the scalp and the electrode that is inside. What are you looking at here is an electroencephalographic, how would you call it? It's the brain waves, if so we want to call it. Obviously, this is our raw data. So you can't see here a P3 just looking at this data. This is just the signal coming straight from the cap. So now I want to show you a couple of things. So I'm going to grab this chair. Do this. Can you please see here? Okay. How do we check if the data looks okay? So first of all, I'm going to ask you to put your phone down and relax for a second. Keep your eyes open. And let's try to find a stable signal. Okay, there is some electrodes there are behaving not too well. Getting better. All right, as you can see now, more or less all the electrodes are behaving as we would expect. Now I'm going to ask you to clench your jaw. Now, the spike that you see here, that's not brain signal. That's what we call muscular artifacts. So they are coming from the fact that when you activate your muscle as every part of your brain and as how the brain works is producing electricity, or a sort of, not electricity, maybe is not the right term, but there is a sort of current. And that's what you see here. Can you try to blink, please? Here we have the same issue. So every blink, you can see the movement of the eyes. So now, how do we act on those? So these are kind of data that we don't want in our signal because this is noise. So one of the things that we have to do, and that's what part of the work you're doing, is to remove this kind of artifacts. So signal processing, part of the signal process is actually to remove this artifact. Now, I'm going to show you something else. Can you please close your eyes and relax? And let's see if you can see something. So what I'm trying to look for, it's when you close your eyes, your brain goes to a certain frequency. This frequency is called alpha frequency. So it's a frequency that is around 10 hertz. And usually once a subject goes into start to relax, it goes into this alpha rhythm. Now it's barely possible to see it here. There is a little bit down here in the. Please, if someone noticed the alpha, please feel free to. I can see it a bit on 6Z, a bit of alpha, but it's not super clear. Do you feel relaxed? Yeah. Okay, this is again movement artifacts. So whenever you run an experiment, what you do is you prepare the subject like this, you hook it up to the EEG and you start to record the signal. But now there is another issue. How do you know when something happened? So let's say you're doing an experiment, you are showing up pictures, but how do we know when we did this show the picture? That it's when the triggers come. So what you can do is you can send signal to the amplifier to say, at this point in time, I showed a picture. So at that point, you can extract that information and cut out time windows from that picture and create an epoch that then is used by our software to create the event-related potential that is the P300, for example. So again, these are just raw signal, and there is still a lot of work to do on it. Till now, most of the electrophysiologists work with averaging. So you take the signal from X number of trial, you cut them up in epochs, and you create an average, and you see how the event-related potential look like. Who knows what the future will tell us more?
Well,
And I think that's for me.
so hopefully we're going to see something on the data. So we get you. Do we want to get them set up over here?
Yes.
And then we can start the experiment. So we'll just grab all the cables, make sure nothing gets.
I'm gonna move this table. And you can.
Do we show the experiment screen or the EEG? Two projectors. Let's give it a go. Can we do?
Change them.
Ah, wait, there's a link button.
Oh.
We can do both. Sorry to our friends on Zoom, you're going to have the projectors in the way. But other than that, we can now show both experiments.
Always remember to click recording.
Are we recording on?
There, but I don't know if
Do we want to do recording on both?
Yeah.
All right, I need to grab.
Sorry. You can't do that on this tablet.
You can go you just go to close down the session.
Okay. Enable.
Oh, will we lose the streaming? Oh, we can try it on the Union network. See if it.
Sorry, technical.
Well, we're going to try it on the Union network. The university IT team is amazing and blocks, quite rightly, random network traffic between two computers that looks mildly suspicious. So they like to sometimes stop us just sending random messages to other computers. So maybe we'll get the markers. We should get the markers on one of these.
Let's see.
That normally gets the marker.
Oops, I got logged out because I look suspicious.
I'll say in the worst case, like all good preparation, we do have ones that we prepared earlier, I believe. So
As in every cooking show.
yeah.
Just show.
Have you got EG signal come through it? Because I've got the stream. Did change it back to that. To re-log in?
Yeah. Probably the best is if I connect to your phone.
All right, hotspot's up.
So I know it's a bit small, but if you want to come and look at it, here is the signal, and we're going to try to record it through the network. So what is happening now? The tablet is sending the signal through the network to that laptop over there, Alex's laptop over there, so that you can record the EEG signal while you do the experiment on the same computer. This is called lab streaming layer. It's a layer that is open source, and it's a sort of system that it's open to use by everybody. And there are some certain systems that support this technology. For example, this one from A&T. And so allows for sending not only recording the signal remotely, but also send trigger remotely. So you can run your experiment in one room and have the recording system somewhere else.
Doesn't look like I'm getting the data from the laptop, but we can just go.
Yeah.
All right. So as an example, we're just going to have you, I'm going to have you look at the screen. So we'll start with the P300. So as before, you'll be shown a string of 10 letters, one of which will be the target character A. So your job is to look out for the A, and that is it. Just try and find the A, don't react, don't do anything, just look for the A. All right, we're going to start 3, 2, 1. Three, two, one. Three, two, one. Three, two, one. One last one. 3, 2, 1. And that's the P3. So
Did I pass?
hopefully. Well, I was going to say, what do the signals look like on there? You've got a brain. That's good. That's good.
Oh my God.
Hang on, is this gonna? What's sending a lot of data now? Feel like doing a couple more of those?
Yeah, go ahead.
All right, we're getting all the data now. Yes. So, 3, 2, 1. Three, two, one. Three, two, one. Three, two, one. Three, two, one. Which data do we want to record? Yeah. I was gonna say, do we want to try and run classification on this, or the data we prepared earlier?
Let's just keep going.
I think we have time. I don't think we have much.
Avinash, how much time do we have? Do we want to keep recording data, or do we just want to use the stuff? Yep. All right. Well,
On this one.
on that one.
Yeah. So just
That's a good question, but
Sorry, what was the question? Be tempted to argue it's actually the opposite, because if we're showing them just a flashing square for 5 or 10 minutes, as the concept up on the screen, participants are going to zone out, participants are going to get fatigued, participants are going to stop focusing hard on the square. So depending on how long you got to do, that's why we normally separate it into blocks to give participants a rest time. Because if we do just do, an example would be we're doing blocks of 10 letters. If we did blocks of 100 letters, I'd presume they'd zone out after like 20 or 30. And at that point,
So, well, before moving to next question, you keep asking, but we have with one of the guests before the lunch, Josh Gordon from TensorFlow. I mentioned that before. So this talk will continue recording this data set. So we continue to discuss this during the lunchtime and stuff like that. So sorry for those who already set up and ready.
I can take the laptop over there if we
Hello,
want.
Josh. Thank you for joining.
Hey, how's it going?
Whenever you're ready, Josh. I think you have access of the screen. Feel free to share and you can get started.
Sure. Sorry, I couldn't hear you before, but I can hear you now. So you'd like me to go ahead and share and get started? Let me see if I can get the right window for you all. Sorry, I still couldn't hear you. Would you like me to get started?
Yes, please get started. That's awesome.
Okay, so hi everyone, good morning. I'm Josh from Google New York, currently in Texas. And yeah, so this will be a quick introduction to deep learning with TensorFlow. And I'm happy to take any questions you might have.
We can't see your screen, Josh.
Oh,
We see something. Now we can see something. Yeah.
okay, let me see if I can make this a little bit easier for y'all to see. How about that? Good, okay. So basically, this is an intro to deep learning with TensorFlow. And if you'd like something more advanced, I'm happy to take questions at the end. And what I'll do is I'll flip back and forth between slides and code. So basically, here's a quick look of what we'll cover. So we'll talk about what deep learning is, and then we'll take a look at a cartoon neural network, and then I'll show you what neurons are and what layers are, and then I'll connect those to code in TensorFlow that you can run in Google Colab. And then from there, we'll take a look at a couple different types of neural networks if we have time, and then we'll look at some educational resources. So basically, as you know, machine learning is a really broad space, and it's been around for a very long time. And what I wanted to show you on this slide is that deep learning is a small subset of the machine learning space. Basically, what deep learning is, it's a type of representation learning. And if you've taken a machine learning class, the big difference with deep learning and other types of ML is that deep learning works really well for high dimensional data. So it's in like 2 sentences. In traditional ML, you typically have something like a tabular data set. This can be something you load maybe from a CSV file. And typically you have a small number of columns for your features, and they're features that you and I can understand intuitively. So for example, maybe you want to predict a patient's risk of cardiovascular disease, and you do that by training something like a decision tree, like you see on this slide here. And maybe the features you feed into the tree are things like the patient's height, their weight, their blood pressure, and so on and so forth. In representation learning and deep learning, typically instead of a CSV file with tabular data, you're working with things like images and text and sound. And these are things with thousands or more features where each individual feature doesn't tell you a lot about the data. So for example, you wouldn't be able to classify an image as a cat or a dog if I just told you the pixel values. It's not something that we can intuitively understand. And so we use neural networks to work with this high dimensional data. So this is a cartoon neural network that I'll break down for you. And basically, it's at the top, you have an input layer. And this input layer is receiving pixels from an image. And I'll connect this to code for you in a moment. So you can imagine that these are grayscale pixels from some image that we wish to classify. And each of these rows of circles corresponds to a layer. So every circle is a neuron, and the row of circles is a layer. And this is called a dense or fully connected layer. And each of these gray lines represents a weight. And this is a learnable parameter that we'll learn via TensorFlow to make this model accurate. The reason the image has been unrolled into an array of pixels is that these dense layers are very simple, and they can only take arrays as input. And so here, the way this basically works, what a neural network does, is the neurons in the first layer are looking at the raw pixel values, and they compute some feature, which is a linear combination of the raw pixel values, and they pass that feature on to the next layer in the network. The next layer is no longer looking at the raw pixel values. Instead, the next layer is looking at the features that were found by the first layer in the network. So maybe you go from pixels, and then combinations of pixels might give you like an edge, combinations of edges might give you shapes, and then the very last layer in the network is the one that's going to classify the data. And what's cool about deep learning is instead of classifying the data in terms of the pixel values, this layer is classifying the data in terms of the features that were found by the layers above it. And so the deep learning refers to a feature hierarchy, and a neural network learns this feature hierarchy automatically. And because there are multiple outputs here, there are multiple circles on this layer, this is a multi-class image classifier. And each of these emits a number, and we would classify the image as the neuron with the highest score. What's really cool, and this is a more advanced example called from an older paper called Deep Dream, or an older experiment called Deep Dream, is that you can visualize the features that are found by different neurons in different layers in the network. And so these are visualizations from an image classifier trained on millions and millions of images. And each grid of images that you're seeing here corresponds to features that a certain layer learned to detect. So each square corresponds to a neuron. These are a bunch of neurons in an early layer. And you see they're detecting edges of different types, so different patterns of edges. If you go down a few layers deeper, you have neurons that are learning to detect different textures, and then patterns, and then parts, and then you get semantic things as well. So what's cool is all of this is automatic. No one programmed this network to recognize these different patterns. It was done completely as a virtue of training the network via gradient descent. So neural networks are extremely powerful, but they're also probably the least intuitive of all machine learning models. And basically, there's a lot of different parameters that you can adjust when you're training your model to make it more accurate. To give you some rough intuition, you can increase the width of the layer. Typically, the wider the layer, you can think roughly the more patterns a network might be able to learn of that type. So a wider layer here would let it recognize more edges, and you can make a deeper network. And the deeper the network, the deeper the feature hierarchy that your model can learn to detect. But again, to be totally clear, nobody understands the type of features that such a model would learn to detect in advance. This is all trained by gradient descent in very high dimensional space. So let's take a look at a neuron and see what's going on there. So this is a little diagram that represents a single neuron. And basically, the circles here on the left represent some input data. If this was a neuron in the first layer of the network, it would be receiving pixels. Or if this was a neuron later inside the network, it would be receiving the inputs from the neurons above it. So anyway, a neuron gets some inputs, and each of these inputs is multiplied by a weight, and that's represented here by theta 0, theta 1, theta 2. And these are learnable parameters. Basically, they're just a number between positive and negative infinity, and the way that these networks work is we initialize them to small random numbers, and then we gradually adjust them over time to make the model more accurate. To make a classification, a neuron takes a linear combination, so it multiplies each input by the weight, and it sums it all up. And right there, you actually have a binary classifier. You could say if that sum is greater than 0, it's a cat. If it's less than 0, it's a dog. Oftentimes, you don't want just a number. You want something that looks more like a probability, or so people often will apply an activation function. What that is that's a piece of math. There's no machine learning, and it squashes the output maybe to be between 0 and 1 if you're using a sigmoid, Or if this is later in the machine learning journey, you might use something like ReLU, which has better properties for gradient descent. But an activation function basically just adjusts the output and it scales it. And there's, I won't go into the math now to keep this quick. What I wanted to show you too is I want to show you another way of looking at these diagrams. And so this is also our neuron. And if you look on the top right, I'm going to build up from a neuron to a neural network. And this diagram has an error in it that I've been meaning to fix. There should be 4 blue circles here because there are 4 inputs and 1 orange output. On the left here, we have a little image, and we're pretending it just has 4 pixels, 12, 48, 96, and 18. And what we're doing here is we're unrolling these pixels and lining them up into an array X, or a column vector X. And again, the reason we're unrolling it is because we're going to make a little dense layer that can only work with arrays. And then we have some weights that are represented by the lines here. And again, there should be 4 blue circles and 4 lines, 4 weights, 1 for each input. And these are initialized small random numbers. And we multiply the weights and the inputs, and we add a bias, and that gives us a score. And in this example, if it's greater than 130, it's a plane. I'll come back to that in a sec. I want to show you how we can move towards something that looks more like a neural network. And so now let's add an additional output. We'll add the purple output. And when we add the purple output, you see how we have, I know it's tiny, but we have more weight. We have more weights here because this is called a fully connected layer. So what we're doing now is we've added another row of weights. We still just have one array of inputs, but we have another row of weights. And so now what we're doing is a matrix multiply. And when we do the matrix multiply, we get 2 outputs. So now we have an output for a plane and an output for a car. So we have a multi-class classifier. And the takeaway here, I want to show you another trick. Let's say for some reason that you wanted to classify 2 images at once. You know, you might have a shirt and a boot. I need to clean up this slide. There's some bugs. But basically, the thing that I wanted to show you is that before, to add an output, we expanded the weights matrix here on the left. But if you want to classify 2 images at once, what you can do is you can expand the inputs. And so what's cool is, even though now we have a network that's classifying 2 images at once, we can still do that with a single matrix multiply. So the point is, basically, the takeaway that I wanted to show you is that when you see something like this, this is called a dense layer. The act of classifying an image with a dense layer is 1 matrix multiply. And that's why things like GPUs and other accelerators from Google, like TPUs, have gotten very popular over the years. And at the bottom here, we're looking at some TensorFlow code to create this network. So what we're doing is we're creating a sequential model. And this is the simplest type of model. It's a stack of layers. There are fancier types of models too, where you can build graphs of layers and stuff like that. But this is a simple stack of layers. We're adding 1 layer, a dense layer, with 10 outputs. So this is going to be a multi-class classifier. And there's different types of activation functions. But when you start writing classifiers, you'll find out that there's really only a few that you need to learn. And one such activation function is called softmax. And this basically says, give me a probability distribution. So when this model makes a prediction, all of the values on these output neurons will range between 0 and 1, and they'll sum to 1. So you can interpret the output as a probability. And down here, I'm writing you a little equation for what this layer is doing when it classifies an image. So it's multiplying the weights by the inputs, and it's applying an activation function to that. And then what's cool is if you want to build something that looks more like a neural network, what you can do is you can add a second layer. So here, this is the TensorFlow code. We have another dense layer. And just so you know, all activation functions that are not the last need to have a different type of activation function than softmax. And typically, it's something like ReLU. Yeah, so basically, I don't want to get lost in the math here, but you can think of another word for an activation function is a nonlinearity. And the reason that we need these on the intermediate layers is so they can learn something that's different than the other layers. So if you look at the equation here, 1 dense layer is just weights, some weights times some inputs. What a neural network is, it's the weights times the inputs for the first layer, followed by an activation function, followed by another layer of weights. And this is the second layer of weights. So a neural network, although it sounds fancy, it's a sequence of matrix multiplies. And if you've taken a linear algebra class and you have a sequence of matrix multiplies, you can reduce those into just one matrix multiply. And what that means is that without the nonlinearity, the layers can't learn anything distinct. So anyway, we need a nonlinearity or an activation function to help the layers learn. Let's see. I don't want to spend too much time on the slides. I want to get into code for you. But also, basically, the point I want to make, this is a deep neural network. And all we've done here is we've added another dense layer. So basically, a fully connected deep neural network, it's a stack of dense layers, and basically it's doing a stack of matrix multiplies. All of these weights are initialized to small random values. I don't have too many slides to go into or time to go into this right now, but basically the way we train this is we take an image, we forward it through the network. We look at the output. If the output is incorrect, we use an algorithm called backpropagation, which basically tells us how to wiggle the weights to make the network slightly more accurate next time. And then we repeat this process many, many times until we've adjusted the weights. So with that said, let me present a different window and show you how to get started with some TensorFlow code. So basically, let me make sure I have the zoom set up properly. Yeah, so I think, okay, perfect. Perfect. So the website that I'm at now is tensorflow.org/tutorials. I'm going to send this to everyone so you have the link. So tensorflow.org/tutorials. And basically, we have a lot of different examples on the website that you can take a look at to get started with. And the one I want to show you today, on the left here, I'm going into basic image classification. And none of this is basic, but this is still a good place to start. So basic image classification. And this is a tutorial that will show you how to train a deep neural network to classify pictures of clothing. And this is a data set with about 70,000 images, each of which is tiny. They're just 28 by 28. And you know, many, many years ago, this was a challenging data set. Now it's very easy, but we like it just because it's good for training models very quickly. In case you're new to this, you can use Google Colab to run all of these tutorials. And I won't introduce Colab right now. I just want to say one point, just in case you are new to it. Colab, basically it's a free zero setup Jupyter Notebook environment that runs on Google Cloud. You can click on Connect to connect to a Colab instance. You can click on a cell and you can run the cell by hitting play or shift enter. So you can run your deep learning code right in the browser. And one nice thing about Colab, although you don't need it for this, you can enable a free GPU, and that will help your models train faster. But I'll just stay on the website for right now and just walk you through some key points, and then you can try this in other tutorials at home. So TensorFlow, it's a Python library with a C++ backend, which helps the code run faster. So basically, we're importing TensorFlow. In most machine learning programs, you'll often see NumPy imported. You'll see libraries like scikit-learn a lot. And then all of deep learning, like any other type of machine learning, starts with data. This is a very famous and small data set, so it's built right into TensorFlow. You'll also see the word Keras a lot, and Keras is a high-level API that makes it easy to define your neural networks. So you can think of TensorFlow as the numerical engine, and Keras is the language you use to talk about neural networks. And Fashion MNIST is divided into train and test. We have images and labels and train, and we have images and labels and test. And basically, if you go through this, you'll read a lot about the data set. And as always, you know, in deep learning, almost all of your time goes into importing and pre-processing the data. Training the network itself is relatively straightforward. So there's a bunch of pre-processing code. You'll often see in these deep learning programs, you're poking around with the shape of data. So what this tells us, if we look at the train images, is a NumPy matrix or whatever, NumPy array. So it's got 60,000 images, each of which is 28 by 28. And sorry, it's very windy in this hotel. And as always, you have one label for every image. Anyway, there's lots of pre-processing code, just importing the data set, normalizing the data set. And after lots of this, finally, we have some code in matplotlib that we can use to display the data set. Great. So after you do all your pre-processing, now you finally get to define your neural network. And this is typically the easy part of writing a TensorFlow program, although it's the one that takes the longest to understand. So this is a neural network, and it's very similar to the slides that you just saw. So because we're using dense layers, we have a special layer called flatten, and flatten's doing the pre-processing. It's unrolling the images into an array. Then we have a dense layer, and the intuition for this is that it can compute features to make it easier for the final dense layer to classify the data. And this dense layer has 10 neurons or 10 outputs because it's a multi-class classifier, and there's 10 different types of clothing. The next step is to compile or configure your neural network. And there's a couple things that look complicated here, but the good news is in deep learning land, there's really only a few different options that you need to learn about. So basically, all networks are trained by gradient descent. There's different types of gradient descent optimizers you can use. A really good one to start with is Atom. And basically, Atom, it's built in. You can use the default options just by passing the string Atom. And it does things like adaptive learning rate and fancy things like that for you. The next thing is you need a loss function. And you'll learn about these as you study, as you progress in your deep learning career. But basically, this is a fancier version of something called mean squared error. So if you've ever heard of mean squared error, if you're doing, if you've heard of something like mean squared error before, basically what a loss function does is we look at the prediction that the network makes, and then we compare that to the true label that we wanted. So you might see something like mean squared error if you're trying to predict the price of a house. And maybe you're trying to use something like logistic regression to predict the price of a house based on things like how many bathrooms does it have, how many square feet does the house have. And what mean squared error does is it compares the value for the house you predicted against the true value for the house. There's another classification function, loss function, that's used in classification problems, and that's called cross entropy. And what cross entropy is doing, it's comparing the output, which is a probability distribution that the model predicted, to the probability distribution that you wanted. So it's a different type of loss function or error function that's useful in classification. And sparse categorical is an implementation detail that you can read more about in this tutorial, and it will make more sense over time. But basically, for now, classification loss. Anyway, when we train these models, neural networks are trained iteratively using gradient descent. So to train this, it's a one-liner. You call model.fit, and you pass it the train images and the train labels. And an epoch is basically a parameter you can set which decides how long you train the network. And what an epoch is, it means we've used every image from the training set at exactly once. So for all of those 60,000 images, they've been forwarded through the network. We make a prediction. We use the loss function to compare the prediction to what we wanted. We use gradient descent to adjust the weights to make the network slightly more accurate. And then we continue on to the next image. And basically, here you can see some output as you train the model. And the accuracy gradually increases over time. And it gets itself up to about 90%. Typically, the next step after you train it is you want to evaluate your models. And you can evaluate them on the test data set. And there's all sorts of stuff you can learn about. If there's lots more tutorials on the website that will show you what to do if the accuracy is too low or too high. And there's basically there's some more details down there that show you how to look at the individual predictions for different images and just inspect and debug the model. So basically, if you're new to this stuff, this is a really excellent place to start. Basic image classification, and you can work through it in Google Colab. And then from there, here's a link you can check out. From there, you might want to learn how to classify text. And this is a tutorial my team wrote a long time ago. It's really nice, though. We spent a long time on it. And basically, it shows you how to do sentiment analysis. And so what this does is this downloads a data set of movie reviews, and you train a model to classify the movie reviews as positive or negative. And what's really nice about this is it starts from just a directory of text files. So it's very easy for you to modify this to work with your own data. And basically, it's cool. It's like a nice way to get started with natural language processing. And you can see that you're working with real world data. So these are some of the movie reviews that you're going to classify. And it's really cool. And at the very end of it, there's actually an exercise we wrote for you. So if you'd like some homework to play with, you could try basic image classification, basic text classification. And at the end of the tutorial, you can do this exercise where you train a classifier to classify Stack Overflow questions. And the goal of this data set, you have a bunch of programming questions, and you try and guess whether the question is for Python, JavaScript, or different programming languages and stuff like that. So those are the basics. And what I'd like to do is just take a couple minutes and show you some of the other cool things you can do. If you're interested in more real-world image classification, you can try this tutorial here. And this will show you how to train an image classifier on a data set of flowers. And what's nice about this is you download the flowers from a zip file. So if you want to modify this to work with your own data, you can. There's other things you can do with images. In addition to classifying them, you can segment them. So this is an image segmentation tutorial where here, I guess we have a cute dog, and we're trying to draw a bounding box around the dog. Other cool things you can play with. If you like audio, we have a cool tutorial that will help you get started with audio classification. And basically the idea here is we have a data set of WAV files, and they're in 10 different categories, like left, down, stop, go, yes, no. And you can train a classifier to classify the audio. And it's really cool. There's a lot of really beautiful things you can do with neural networks too. So this is an example of a type of neural network called a GAN, or a generative adversarial neural network. And in this example, what you have is, this is actually a conditional GAN, but you have a input image, which corresponds to maybe a block diagram of a hotel. And what this model does is it synthesizes an image that corresponds to the hotel that you're looking at here. And what's cool is for every single tutorial on the website, if you run the tutorial, this is the output that you get. So it has the complete code to do everything you see here. There's other things you can do in deep learning that's pretty cool, like adversarial learning. And this is a example where you're trying to fool a neural network. And what we have here is on the left, or trick a neural network. We have an image of a panda. And what this tutorial does is it finds a special type of noise. And if we add this noise to the image of the panda, we get out another image that to you and I still looks like a panda. But if we classify this with the neural network, it will say that it's looking at a monkey. So this is called an adversarial attack. And it's a way to fool a neural network into thinking it's looking at a different type of image. Let's see. If you're doing things in business, oftentimes you're working with tabular data. And I mentioned that often for tabular data, the best thing to use is something like a decision tree or a random forest or a gradient boosted tree. And as it happens, TensorFlow actually has a library to work with gradient boosted trees as well, which I put into the chat. But you can also use neural networks. And this is a really cool data set. It's from Kaggle, and it's a credit card fraud data set. And the idea is you have a bunch of features that represent a credit card transaction. And your job is to figure out whether this was legit or fraud. And you train a neural network to do that. We have other examples of working with tabular data and neural networks as well. So this is a data set from Pet Finder. And the goal is to predict whether a pet will be adopted based on attributes like the age, the type of pet, and whether it's been vaccinated and stuff like that. So this is just a big tabular data set. You can use neural networks for that as well. Let's see. Anyway, there's all sorts of cool stuff you can do. If you're interested in the very latest things that have happened with deep learning, what you can do is Google for Imagine Google Research. And what that is it's a deep learning program that will actually synthesize images. And it's quite beautiful. So that's like a very quick overview of deep learning. And let me give you some educational recommendations, and I'm happy to take any questions you might have. So if you're interested in learning more about deep learning, the very best book I think that exists today is this book by Francois Chollet, and it's called Deep Learning with Python 2nd edition. it's very important to get the second edition because this teaches the latest version of TensorFlow and Keras. It's excellent. I use it as one of the books in a class that I've taught for many years, and students love it. So it's a really excellent book, Deep Learning Python, second edition, and that's pretty much all you need to get started. It's really excellent. So yeah, with all that, I'm happy to take any questions about deep learning or anything in general.
Thank you, Josh. Thank you. That's a great packed tutorial. Thank you for Josh. I know it's like a 10 or 11 a.m. Sorry, p.m. there, where you are. So thank you for your effort.
Yeah, sure.
To make us.
Thanks for having me.
So if you have any question, that's the right time, or we always can discuss later on. I'm not have a bit of background in machine learning. If not, that's a very packed tutorial. But we're gonna go through with more TensorFlow after this session. So whatever you kind of get here, you're gonna try your hands-on on the Google Colab itself. So it will make more sense after that, hopefully.
It takes about 6 months to learn this stuff. It takes a long time. So yeah, take your time with it.
Exactly. And
I'm a scientist and I'm terrible at programming.
I heard the first half of your question, but not the second. I heard I'm a scientist and that's it.
Okay, I'm a biologist and I'm terrible at coding, but I'm getting excited about AI because it's starting to seem like the barriers to me accessing the powerful processing are getting lower and lower every day. And I'm wondering, when I'm designing data sets, what are the most important things to think about? Like when I'm designing an experiment and I say, you know, I'm going to have huge amounts of data that are going to be difficult for me to process, but I know that this is the type of deep learning might be able to solve it for me. I saw in that thing, the data set that we got given was very famous. When we're designing data sets now, what are the kind of parameters and attributes I should be thinking about to design an experiment that's good for a deep learning processing?
So that's a really good question. I'm not sure I can answer that in one sentence. Basically, I love that you're trying to apply deep learning to biology. My advice would be make a friend or find a partner. So deep learning is often a team sport. And what you might find is that in the computer science department, there might be lots of programmers who are really interested in biology, but they don't know anything about biology. That would be somebody like me a long time ago. And you might be able to partner with a CS student, you know, to work together. And that's my best advice. But when you're designing a data set, I guess the thing to think about would be, what's the problem you're trying to solve? And is the input data that you have sufficient to solve the problem? We'd have to talk more offline. I don't know enough about biology to give you a good answer. But anyway, in general, large, high quality data sets are very important.
Thank you, Josh. That's kind of answer what Meow is asking. And anyone have a question? So Josh on Twitter, I think pretty active there. So you can also ping him there. I don't know. That's a good way, Josh. Or
Yeah,
you always can go through the Google tutorial, which is pretty nice and pretty good to follow up, and the book, of course. So again, thank you for Josh again for joining. Thank you, Josh.
Thanks very much for having me. Have a good day, everybody.
And have a good night to you.
Thanks. Okay. Bye-bye.
So this is the point where we have actually lunch, but same time you guys can discuss, and we can also record multiple things same time. So we have like 45 minutes from now on before we can get started. And from now on, whatever we do more hands-on. So we're gonna provide you some links to download, specifically this Google Colab, and we focus on EEG signal only. And we talk about bit of metadata and the gap we're talking from the morning. I know this is a quite compact everything in a short time, but that's the whole idea as well. So kind of expose you in a short time, lots of things, which kind of give you a thought afterward, hopefully. So feel free to move around, and we will pause for online as well. until we come back, which is around 1:15. You guys.
Yeah, I mean,
yeah, so basically, I mean, the whole, yeah, so time series, time series. Right. There's this one processing chain.
Forks. Oh, oops, thanks. Basically, this study, what they did is they applied each step I outlined before, and then they basically applied it in a range. So they tried different frequencies and different sort of lengths of epoch, different references, things like that. And what they found is there's actually, yeah, there's going to be a wide range of probabilities of what will turn out. And when they do a statistical analysis on those probabilities, they actually found that some signals will have statistical difference between each other. So what that tells us is that actually what you put into your parameters for pre-processing will definitely affect your final result. And that's quite intuitive, but it's something that people often don't talk about when they do data analysis, or even when you're just looking through literature. So I'll give you guys a bit of a case study or one example on how we're going to do this. So I've actually collected 2 data sets a while ago. So let's just hypothetically say one data set is condition 1, one data set is condition 2. For context, condition 1 is when you looked at a P300 oddball task on a monitor. And then condition 2 is I got someone to wear a VR headset and do the same task on a VR headset. So if you remember sort of the oddball task or the P300 task Alex talked about, it's just the one with the blue and green circle. So that's my one. The blue circle is the target. And basically I'm going to play circles at 800 millisecond intervals. And then when they see a blue circle, that's when they recognize the target image. So we're going to say there's 2 scientists. One's going to be called Sonic. Sonic claims that there's no difference between 2 conditions. The other one is called Ugly Sonic. He's going to claim there is a significant difference between the 2 conditions. All right, so let's look at their claims. So what we do is we're going to take the same data set and apply the methodology they used. So I'm going to quickly use an app that we built. So I'm going to share you guys the link for this app later. But this app, hopefully will work. Well, hopefully the technology would work. See if we can see this. On my neck. Here we go. Okay, so this app I'll show you guys at the end of the slides. But hey. Let's try that. All right. So what we'll do is we'll load the 2 data sets. So data set 1 and we'll data set 2. Okay, so then we'll basically apply each Sonic steps. So Sonic 1 said it was going to filter 1 to 50 hertz. He's going to reference to a common average. So that's taking all the channels and averaging the value and then using that as a reference. And then he's going to downsample to 256. And then he's going to epoch at negative 500 to 1 second, basically, or 1000 milliseconds. So we're going to look around the target event and we're going to see how the data looks. So this is what we call event-related potential waveform. It's quite simple. It's essentially just the amplitude on the channel, just plotted in the epoch in a time zone, in a time frame that's referenced. Okay, so Sonic 1's claim is good. So he's saying there's no significant difference. And if you look at the p-value, indeed, there's no significant difference between 2 signal peaks. All right, so then let's look at Sonic 2's sort of claim again. So Sonic 2 claimed he used 1 to 100 hertz for the filter range. And then he didn't reference the average. So he just referenced to the default reference channel. Scientifically, I can't really argue with why that will be wrong. There are some factors in some papers that claim that's not correct. But again, in the scientific community, you'll probably find a split between people claiming certain things. Here we go. Apply Ugly Sonic's pipeline. Oh, look at that. So Ugly Sonic just changed 2 subtle steps, but now he's finding a p-value of 0.004.
So that's quite high of significance. So it's actually saying these two are actually a significant difference between each other. So we can see how these little simple sort of digital signal processing steps, just some basic steps of filtering, can actually change the significance on it. So then how do we reconcile these two, right? So a simple answer will be, okay, let's look at the papers. Let's look at what the literature says, right? So I took 3 papers from all peer-reviewed, generally I would say they're pretty top-tier journals, fairly well-established journals, and looked at their methodology for P300 analysis. So, okay, this journal says, oh, I'm going to use 0.1 to 12 hertz. So that's a smaller band than both sonics. And he's going to downsample to 36.6 hertz. So that's quite a small sampling. And then they're not going to use epoch at all. Personally, again, there will be some issues with that. But what they will find if they apply that is they won't find significant difference. Okay, let's look at the next study. The next study goes from 0.01 to 100 hertz. And then they sample at a higher higher sampling rate EEG device. So they use 1000 hertz on their EEG device. And then they re-reference to the central channel. So usually, for example, Ugly Sonic, if he said no re-referencing, then he will reference it to the voltage on the FCZ channel, which is sort of on the center frontal of the head. And people do that because they think, okay, the skull cap is thickest there, therefore I'll reference to that point. Some people reference to CZ. Again, there are subtle differences in literature, but no one will argue against doing that. And then they epoch between -200 to 1 second, basically. And then the final paper basically uses Ugly Sonic's methodology of filtering to 1 to 100 hertz, and then uses downsample to 250 instead of 256. And then they reference to average. And then they use another epoch range that's slightly different. So what we see is like you'll find a lot of different literature uses a lot of different methodologies. And it's very hard to sort of contend with this when you see people using different steps that's logically still sort of abiding by the guidelines. So to give you an idea what's the rationale behind each step, I've sort of highlighted a lot of the sort of factors that goes into each step. And this is only 4 steps. So if you remember in the previous slide, there was about 8 to 9 steps that could be involved. And these steps branch out the possibilities even more. So even in the 4 most basic steps, you will have a lot of factors involved. So one factor for filtering you need to consider is brainwaves. So as sort of we hinted when we tested the raw data, you can see there's something called alpha oscillation. And there's actually beta, delta, theta, and gamma oscillation too. These oscillate at a specific frequency. So often when you're considering how do you want to filter, you need to think about, oh, which ranges are you looking for? What effect you're looking for? So for example, if you saw the other guy with 0.06 to phase 6, or even less, I think it was 20 or something hertz, he's going to be losing a lot of beta and gamma waves out of that. Other things you need to think about is line noise. So there's noise from the DC line. Anything electronic will have line noise. So that's just the steps going to bandpass filtering. Each step, like sampling rate, again, you have to think about a lot of conditions on how you want to do computational time. You got to think about factors of Nyquist frequency. So that's another sort of digital signal processing step. And then even with referencing, where do you want to reference your electrode voltages? So there's actually, when you look at this, there's quite a lot of steps and there could be quite a lot of variance as we sort of highlighted. So I'm going to leave it to the final point, which is how do we reconcile this? So one of the things initially when I was developing this is I want to just say, Sonic is right. So I want to just tell you guys Sonic is right. I'm going to pull up a bunch of literatures and spend 5 minutes convincing you Sonic is correct. You should follow my way. But I realized that was very hard because I was trying to, even on the first step, I got stuck. I was trying to convince you guys 1 hertz is the best way for a high pass filter. I found a few papers that said, yes, 1 hertz produces the best signal. It gets rid of slow noise. And then I'll just find another 5 papers that claim, no, it should be 0.5 hertz. It should be 0.01 hertz. And as we see in literature, there is still variance. And these people are the ones that would basically be diehard claiming, no, the high pass filter should be this range. And then, so I go, so let's just say 0.1 to 1 hertz. And then I looked at 50 hertz. I said, okay, 50 hertz is a line noise. And then again, you'll see papers saying, oh, I don't need to look at gamma waves and things like that. I just need to look at alpha to beta. So I found that at every step, I could find a bunch, like 5 or 6 papers claiming one thing, and then 5 or 6 papers sort of refuting that, and then another paper coming out to refute that again. So unfortunately, I can't really leave you guys with just here's the golden equation to use. I really tried to actually leave you guys with the golden equation, but I couldn't find it. So I'll leave you guys with this sort of advice. One is whenever you're developing a pre-processing pipeline, try to always follow rational fundamental signal processing principles and the understanding of neuroscience. So try to read up about the brain waves, try to read up about each step and why we do each step, and then read those papers that argue with each other and understand why these papers are arguing with each other. The next thing is, I think for a standardized approach, there still needs to be that wider conversation with the neuroscience community where people need to continue. It's good that people have conflicting results because that means we're discussing it and we're discussing what is the right methodology. Final one, this is more for if you're really into trying to build cognitive neuroscience pipelines or really into that kind of EEG data analysis. I've attached a link. This is called Makoto's pre-processing pipeline. Again, this is not the golden equation. This is basically like a forum where people discuss what is the best way to analyze data. So you're going to find a lot of sections. A lot of it won't make any sense, but once you start reading it, you can start rationalizing how each person gets to each spot. And the last thing is try it yourself. So I've attached the link to the tool I demonstrate on how to actually analyze the ERP for P300s and play around with each step. With this tool, there's actually quite a few things you can do. You can change the ordering of each step, so you can rearrange the ordering. You can change the parameters, so you can change all these parameters to whatever you want. And there's quite a few things you can play around with. So I'd recommend first-hand experience is still always better than just reading. So try it, apply different methodologies, see how each works out, and see how it goes. Yeah, I think I sort of went under time. So I'll leave it back to Avinash and he'll show you guys how to do the data analysis. So.
Thank you, Howie. Again, this is another example where standard is super, super important, right? Because if you don't have a standard, you just do whatever you like. And because you do whatever you like, you can have desired result, which is okay from your point of view. You have, if you're a researcher, it's good for publication, maybe good for some other stuff. But making a real impact required a more group effort or more standard effort, which is shareable, repeatable, a more follow the FAIR principle. And that's not possible without standard. So pipeline is another issue. I'm gonna stop this presentation, and this is very tiny example, really. We are not really getting any, none of these things get too deeper because just want to give an idea. Some simple ordering. So those who are in cognitive neuroscience, they have to process signals. And that's where this pipeline are super essential. And these are very early step in the pipeline, not even reach the complicated stuff where you remove the noise and enhance the signal quality and stuff like that. No, we are not even talking. We're talking about band pass filtering. We're talking about resampling only. And it just changed the whole result, how the signal look like. And that's what you will see in the paper. And that's a bit of problem with EEG community. Well, I think it's not just EEG, maybe fMRI and all neuroscience, maybe beyond neuroscience actually. But we are talking about neuroscience here today. So now what I'm gonna do, I'm gonna move from here to a bit of metadata. Why that important? So pipeline is from neuroscience point of view. Metadata is for more machine learning point of view, where if neuroscience community, rather than hiding all the information, what they did with the data and give you the result only, if they just give more details, and how they can give you more details is if they follow certain standard, then the whole life of this machine learning processing will become very easy. And what I'm gonna give a very tiny example. Let me think. I'm gonna put just something here. Let me replicate my window here. So I have a data set which we just recorded today. And also we have recorded a few data set from the same device yesterday in the evening, just for demonstration only. And of course, size of data set, especially in EEG, is too little. What we did, P300 required bunch of repeated trials. We hardly did 20, 30. Same for SSV. SSVP is comparatively better, but what I'm going to use is called EEG Lab, the tool which is very popular among EEG people. And it's an open source tool. You can download it, work in MATLAB. I'm gonna use MATLAB. So of course, if you have MATLAB, you can also feel free to do that. But what I'm going to show you, let's say this data set. This is the data set we recorded from forcefully on one intern yesterday. He's happy to do that, let's say. Now, if you see what EEG data is all about, it's a continuous time series. Okay, it's just long data. If you record for 1 hour, it's just continuous time series without any clue where things start, where things end. And now think about if you're a machine learning expert or researcher. If you have no clue what's happening in the data, there's no way that you can even feed in your model and do some classification. Well, to do that, of course, there's a one way that researcher like us, I mean, we are more in neuroscience, we record these labels. You see 0, 1, 0, 1, 0, 1. They represent what's happening. So 1 represent P300, 0 represent no P300 here in this case. But what I'm doing is using EEG Lab, which is a tool more for neuroscience people, right? I think I forgot sharing screen. Sorry for that. Just quick recap. I uploaded the data, showing the data here from EEG Lab, which is a P300 data set. So like I said, data set is always continuous time series. So what you're seeing here, these blue lines is actually our data coming from headset, recorded from ANT, and these numbers represent the sensor or channels which you on your head. There's total 64 number of channels. So you can see 64 on Y, and X is like a, I think we recorded like 5 minutes, and the sampling rate here is a 1000 hertz. So that means every second we have like 64,000 data point, which is very good for machine learning point of view. But again, because you people who are not familiar with EEG Lab, they can't see this, what's happening here. And because you can't see it, I mean, of course you can see if you go and learn this tech tutorial, go dive into domain knowledge. And that's where the gap comes in. Not everyone want to do that. Someone want to just try out the algorithm with bit of less effort, which is okay, because you want to focus on algorithm rather than neuroscience, for instance. So what can be done for this step? If there's a tool, let's say I provide this data to openly for everyone. Of course, EEG Lab, you don't know, or machine learning researcher or programmer have no idea how to use EEG Lab. But there could be a tool that can give you a data into the format which required easily feed up into machine learning algorithm. Doesn't matter, TensorFlow or any deep learning or any platform like a Weka, like Luigi is talking about in the morning. He showed one example. That tool is still in development. I am also going to another example. And for this P300 task, what I need, a very simple information. If you see here, it's too small though. Here, let me try. All right, buttons doesn't work. Well, what you're seeing here is say trial duration equal to minus 0.5 to 1, which essentially mean how long the user is seeing the stimulus. This is very simple metadata, but it's always unavailable when you go for download the open access data. When I say unavailable, it's available in literature. If you go through the paper, read them, what they did, yes, it makes sense. But again, to understand the paper itself, another effort. And that's why I'm talking about it shouldn't be there. It should be feed up in the data set itself. Just having this tiny information, what is possible to do? Let me show you. So I use the data set 1, which is one of the recorded one. There's a target, non-target, which represent P300, non-P300, and just run this thing and let's call it test. But I'm creating a mat file. Essentially, you can create text file, vector file, whatever you like, really, if you have just tiny metadata information. When I run it, I got a data set which look like this. It's a 3-dimensional. Wait, hold a second. You don't need to learn MATLAB if you don't know, but I'm just showing you. Okay, so what you got, if you see this dimension, it's a 750 to 250, where 750 represent number of sample point and 250 is your number of trials. So you have 250 trials, and out of 250, I think the other 50-50, it's not 50-50, 30-70, 30% data is belongs to the label target, 70% data belongs to label non-target. And this data can be fed very easily with any of the tool, especially when you talk about, and you don't need to take care any information which is non-essential or non-domain related. Another thing I want to show is, for example, this is labels, again, which is very, very important when you talk about machine learning classification. So you see 000, which represent a non-target, or I think target, no, sorry, non-target, and 1 represent the, I think it's opposite. 0 represent the target, 1 represent the non-target in this case, because 1 are more. So one tiny information, if provided as a metadata, it just make a big difference. That's what I'm trying to mention here. And that's why, again, standards are super essential. Now, I'm gonna hand over back to machine learning people where they feed this data to show you how to make this work in Colab. So where's Sunny? Sunny and Regia. Feel free to ask any question meanwhile. I'm gonna quickly download this slide.
You, Avinash. And I hope you guys had coffee before coming to the session, so that we are not sleepy or I'm not boring. It goes both ways, right? So we bring you the hands-on session where you can experiment whatever theory you have learned until now with some bit and bite-sized eatable chunks of machine learning on BCI specifically, right? I'd like to say thanks to Legia, who's sitting in the back, and he will join me soon for presenting most of, or preparing most of the code which you are going to run. Sorry. Screen share. Can you stop share and share again? Oh. Yeah. Well, for us, it's fine, but for the people online, they were not able to look at the screen. Or is it available now, right? So yeah, going on. Thanks, Legia. And now I'm just presenting the slides. Also, I will take you or walk you over what happens with the code and how to set up things. But it's just a short demo here. And the world is very big in terms of deep learning, right? So, what are the steps in this demonstration? Is the first step, we would be using a setup, and the setup is called Colab from TensorFlow, which Josh already showed you this morning. The reason why we chose this, because most of us who are here are not experts in hardware and setting up the network. So it takes away all of the pain. you can just use Colab on your browser, but it's a free tier, so it has limitations. If you want to purchase a pro account, it's not that expensive, and it gives you plenty of options, which is optimized GPU resources and other stuff. After we have set up our environment, we are going to generate a P300 dataset, which Avinash was talking about. And we are going to visually interpret the data. How does the data work? The data is over multiple dimensions, and there's so many data points. So for humans, our brains, although they are big, but our visual understanding over thousands of dimensions is very small. So how to crush all of that into some readable, understandable format is the key. And after that, we are going to train a demo or a basic neural network on that P300 data set. And then we are going to benchmark the performance, what we have done. And lastly, we will try something which we have captured earlier today, right? So simply steps 1 and 2 in the notebook, which I will be sharing now, is on Colab. Your P300 is, or the data set we are going to try is from M&E Lab. It's a Python API or Python software by some BCI experts. Am I correct, Avinash? Yep. Then for visual understanding, we are using matplotlib, again, a very famous library among data scientists. Then for training, it's TensorFlow and Keras. Keras is again a product of deep learning or Google, which came out of same TensorFlow team, but it takes away, again, a lot of pain from software engineers to just practitioners who want to try and understand things. And lastly, we will try a demo on the data which is recorded earlier. Now, to access the notebook, can you go to the link, which is tiny URL, UTS BCI workshop. So let me also go there. Yep. So please just follow this one, tinyurl.com, UTS BCI workshop. Easy, right? If it's not visible, then I can, where? Okay, let me try here. tinyurl.com, UTS BCI workshop, right? Here we are. So just to connect with my peer sitting at the very back, Legia, did we updated our code? Right. Sorry. Just come over here. It's okay. So Legia is a bit shy. So why don't we try to cheer him up? Right. Did you send him the
Yeah.
right? Okay.
No, this one. It's good.
Sorry.
It's good. I think it's good.
Is this one or wait? Let us just confirm something. Maybe for the moment I will try to stop sharing because I don't want to embarrass myself, right? But have you guys reached the Google Drive? Anyone who's not able to online audiences? So yeah, just upload. Yeah. So let me share the slide again. My apologies. There is a bit mismatch of the versions which we prepared. So while the version is being set up, let's try at least the demo. So to start Colab or to utilize Colab, you should have a Google account, a Gmail account. I believe everyone has it here, so it should be accessible. If you have any errors, please talk to Avinash or Legia or just raise raise your hand. Avinash, can you take care of questions? Oh, Can you share the link on the, or I can type tinyurl.com UTS BCI workshop. So as I said in my slides, the first step is to install the versions. Right. So let me just quickly
Okay.
change again the right version, right?
Yeah, let's try. Let's see.
Okay. And I'm gonna close the previous version. So you guys can also just try and load the new version,
Let's try.
right?
Think of what.
If you want to again.
Yeah, try. Check. Let's see. And the accuracy.
Yeah,
that's correct.
right. So we have the correct version now by verified by our famous doctor Legia, or doctor to be, right? But the energy in the room is very cold. It's just me listening to myself, right? So please, I appreciate if you guys also communicate with us, right? Oh, yeah. See, it's either Avinash who's speaking or me, right? So I just try to increase the font size so that it's visible, so that others can also view it, onto the audiences, right? So now comes the part where we have spent our 3.5 years of PhD scratching our head, trying to scratch our hair, pull it out because there was so much or a gap to start the process of learning deep learning. But we have taken all of those things out of the box today to give you a good memory of this workshop. So first, the prerequisite is to install some packages, scientific and also visualization packages, such as MNE, which is for EEG data processing, NumPy for numerical computing, SciPy, Matplotlib, that's a famous visualization library, scikit-learn, that's general purpose machine learning library, and TensorFlow 2.0. Now, Colab, when you start a Colab environment in your browser, most of the packages are pre-installed, so you don't need to worry about them. The only thing you need to install externally or by your force is MNE, this package, right? And other packages can be imported. Now, I don't know how much you guys are familiar with Python. Who's using it for the first time? Okay, there's one guy who at least have heard about scikit-learn or Matplotlib. Well, quite a few. So you guys already tried some demonstrations? Yes, no? Yeah, right, okay. Now, I think we need some BCI to understand your head pose movement, right? So that we can try. Yeah? Maybe he's a good person to put some to take his data and try some BCI learning on it, right? So yeah, exactly, definitely, yeah, right? So we can understand what's going on his brain. Is it a yes? Is it a no? Or maybe, right? So yeah. So jokes apart, let's try to run the first cell. Now we are gonna work in this is not a software engineering class. This is a demonstration environment. So we are gonna make things maybe look bad when we have implemented it, but we have made it readable and understandable for you. And it's not packaged really dense, it's loosely packaged. Each of the components are loosely packaged so that you can easily tier them and stitch them according to your own needs, right? So how Colab or an environment on a browser works, it has some cells where you can think of a cell as some instructions, which you're going to write, and the browser can read those instructions and try to run it. So if you see this highlighted section, it's a cell. Now, Colab provides you two kinds of cell. One is a text cell for your comments or instructions or your notes. And the second one is a cell where you put your Python script or code. So to start any cell is very easy. Either you click a code and you can type your Python code where this is gibberish. I should say maybe a = 5, right? Just a primer, because we have someone who is using Python for the first time, right? So a is a variable and the value is 5, right? So I just executed the cell by just clicking the play button on the left to it, and their army is here, right? Oh, it's taking a bit of time to run, because for the first time it needs to connect us to a backend environment, which is connected with TensorFlow and all of the libraries. Now we can look at this variable a by clicking over this x, which is written in italic and Euler form with some brackets. If we click that, which I can't see anything over here, but now we can see a is there of type integer, and the value of a, which is a variable, is 5, right? So I can walk over different things here, right? The second cell is a text cell where I can say, okay, just playing with the syntax, right? This is just for your own understanding, so that you don't forget what you have done. This and Colab provides markdown, such as if you want to increase the font size or make it bold, right? Or make it italic, or provide some list over here, such things. So just play around and get familiar with it. I will now quickly run. Avinash, please let me know if we are running out of time, because I talk a lot. Sorry. So we will install MNE and TensorBoard package externally. And in normal Python environment, if you have something locally on your computer, you would just say pip install MNE. But for Colab environment, you need to put an exclamation mark before the instruction, so that it can understand that it needs to run it and install something. So just by clicking the play button once again, it's gonna install the packages, EEG data package and the TensorBoard. TensorBoard is just there for us to see what kind of network we are training. Any problems do you know? No? Oh. Do we understand what's PIC? Sorry? Right. Okay. Yeah. It's just, we don't want you to, feel scared when too many warnings arrives on your screen and you get and you lose track of what's happening. So we just try to switch off the warnings so that you just focus on the code and the output and the analysis. Now, again, we have installed many things, but to use them, we need to import it. Import it simply like I have my laptop in my bag, but I need to bring the laptop in front of me to actually start it, right? That's what it is. To draw a PowerPoint, to make a PowerPoint presentation, I actually need Microsoft tool to be installed in my computer, right? So those are the things. We have make the maybe Avinash, you can take care of the comment, right? On the chat. So now we are simply importing things for us, such as I already said, we need TensorFlow and Keras. We need Matplotlib to visually see what data we are using. and MNE, which is our EEG data laboratory. Right? Now, it might take a while depending on your network, which we all are using the same network at UTS, so should be fast. But now comes, now before we actually go on and try some machine learning, the 101 is that you should reproduce what you have done, such that if Avinash comes and says, oh, I have produced a very good machine learning model, who can read anyone's, or who can do the excellent job on BCI, and the moment I try to put a reset button to that and start the things again, I'm unable to recreate what he has done. Okay, so that's why we need to make sure that whatever state, whatever normalization techniques, or simply whatever steps he has taken, those steps are deterministic. We can take the exact same states whenever we push a reboot button and do the things once again. So for that, we are setting a seed. So whenever there's any randomization, that randomization is gonna follow this particular seed. So that we can always recreate whatever has been done earlier. So, yep. And now there are some parameters. This where the fun part is coming. We are just explaining things before you actually try the neural network, such that you are able to break down things on your own and then do some additional steps. Right? So few things is EEG sample count. This is the number of samples we are gonna try from MNE dataset to train our neural network. What's the learning rate and how fast or how slow the deep neural network should learn? If you recall what Josh said a few hours earlier, that the disparity between prediction and the ground truth, how fast you want to converge these two depends on the learning rate. An example, this workshop is going from morning 9:30 till now, and we are putting everything to you over BCI in a condensed format. But Legia here has spent his 3.5 years understanding BCI and the nuts and the tricks and other things. He have much better knowledge because he learned those things over a broad period of time, right? So that's the learning rate. You can be a doctor in 3.5 years, or you can be an analyst in just 1 day, right? But not a doctor yet. Soon, yeah, no worries. So then we have the sample length. Now, Avinash, do you want to speak? What's the difference between sample count and sample length? Right. So does each try should have equal sample length? Why? And what should we do to identify that we have the same sample length in each trial? What steps you take? Yeah, right. But when you import, but when you import data, you usually have a matrix format, right? So at least my assumption is correct. You guys know a bit of mathematics, high school mathematics. So you have a matrix, and in a matrix you have fixed dimension. So the rows are sample count and the columns are sample length, and sample length is going to be equal because it's a matrix format, right? Of course, there can be missing values, corrupted values. That's a separate devil. Now, number of classes in the EEG dataset, we are going over the very basic, which is either positive or negative or 2 classes. And in machine learning, we have a standard terminology for that, which is binary classification setting. Now, hidden 1, hidden 2, hidden 3, and output, these are parameters specific to the deep learning layer. As Josh was saying, that we have some high layer, which is processing all of the features, passing it to the second layer, then the third layer. Now, how many neurons or how many data points you want in a layer is specified by hidden 1, hidden 2, which is 500, 1,000, 110. This is what our expert here thinks is good enough for this demo. But you can always play with it. Instead of 1,000, you can make it 800, or you can make it 700. So first hidden layer has 500 features, then it's expanding it to 700 features, then it's reducing or squashing it to 100 features, then to only 10 features, and so on, right? So I'm just going to go with your settings, right? And we can again run them and see whether or check their value as a in our browser. So we can see sample length is 226, what Legia has kept as a constant, and I think that's what M&E software requires, right? So you also need to look at other libraries you are importing, such as I already told you matplotlib, right? So this is one library where you can look at these visualization, how to create a sample visualization, maybe histogram plot, what's the input type, and how you're gonna specify the data. It's just a function, and the parameters of the function you can look through other libraries where you are utilizing. Take the, you wanna present some? Why not? Please. Yeah. So presenting Legia.
All right. Let's continue to gather EEG data from the M&E package. First, okay. First, we need to define the data path here, and we run it. Okay. And to firstly download the data sets and return the direction the directory of the data set. Okay, that's a way.
So any problems under this cell, or you guys have already finished everything without us taking you over?
Wait the data set to be downloaded. Yes. Yeah, 1.6. Okay. I'm sorry. Yeah. Thanks.
Also, another important point, whatever you download in Colab gets squashed or is flushed the moment your session terminates, or the moment you terminate your session. So on the right hand side, if you see you have some RAM and disk located, Legia, can you point to that one?
Which one?
The RAM and the disk. Sorry, on the right side, right? So you are connected to a hosted runtime environment. The moment you disconnect, the moment you terminate your browser, all this data is flushed. There's a way to permanently store data, which is putting all your data to your Google Drive and connect your Google Drive to Colab so that they can communicate, do the writing or reading of the data. Right? Can you admit this one? Just admit. Yeah, that's okay. Yep. So we have downloaded the M&E data and specified a data path, and the data path is here, root M&E Python JSON. So why don't you show them the path of the data, Lydia? Yeah, show them the path where the data has been downloaded.
Here
Yeah.
you can check the data here. This is the default directory, and we can go to the upper one and check this data. It's like a root. You can find the root here, and we check the MNE data here. Let's see, we can get the data over there.
So can you find the data in your own browsers? Oh.
Okay, cool.
But how about the right side? Can you find the data in your browser? Those who are following. Okay, thank you.
Okay.
Sometimes I don't wear my glasses, so if you're raising hand, I need to wear it for. I mean, until I'm presenting. Yeah, go ahead. No,
Okay.
present.
All right. Once the data is downloaded, and we will extract the P300 data here. It's like we define the data path here, and we run it. This is the overview of the data here, and
Right.
yeah.
Right. Maybe just also tell them that it's not or you can also choose any other path where you want to put the data. For that, just stay here. I'm not hijacking your presentation. So you guys can create a folder. I think it's gonna be in content. So you guys can always create a folder. Let's say you want a new folder and say M&E data maybe. Data. And so by this, you can always now copy all of the data. And I think it's CP command for copy, those who are familiar with the terminal. So whatever is in data path, am I correct with the command? Right. Well, if I'm wrong, then we will figure it out how to work it, right? We want to copy everything to M&E, this folder. Now I just copy the path and maybe paste it, and maybe R for recursive, right? Yeah. So let's try. And it says there's no such. Right. Sorry, my mistake. Oh, it's again. So Lydia, you wanna help me? So how about we see try to check whether our path is correct or not. So this command, it's not correct. Okay, so how about we print it? What's there? Okay, so let's say I take the absolute path instead of some relative path, and the absolute path, it's root M&E. Is it dot, I guess? I'm sorry. Just bear with me. I'm trying to, try to show that even as an expert, you fail and you try to fix the problems. Where it's running. Let's see whether, yeah, I can see something got copied and all of the data is in my, under my content folder, right? So now you can also specify this as a path. So just showing you, trying to give you more interactive hands-on with Olab. Back to you.
Okay. All right. After we get the overview data sets, okay, so we can then extract the EEG P300 data through this line. We can pick the tab. It's not here. No, it's the wrong line. Should be this line. Okay, we get the EEG only data. This is the positive labeled data. And then we need
Wait. Why don't you try to ask them question? You are the architect of this code, right? You know everything, but the
Okay.
audience don't.
What should I ask?
Just pick any person you want and try to ask him question. Don't scare him, he will run away.
Okay.
This is a free workshop, he hasn't paid,
Okay.
right?
That's-
Or you wanna help me to help you?
Yeah, sure.
Want to ask question? Maybe that guy, Alex, or the guy next to him, or maybe Avinash or Yanchu. Oh, Yanchu, sorry, he selected you. Yeah, I'm sorry, right? I take you over coffee after this one, but he's the person
Okay.
whom we should beat. So, yeah, first, what question should I ask her? Yeah, well, anyways, to understand what's set EEG reference as a function. Last question to him, right? So what's set EEG reference function, Legia?
All I know is that you gather data.
Okay, but wait, is it, I don't know whether the audience want to know what set EEG reference function. Do you? Of course, even I don't know. I was trying to get an answer, but are you interested in getting an answer, or no, we should just move to TensorFlow? Yes, it will. It will work if you don't know. I think what's happening with set EEG reference function is he's printing all of the parameters the data was recorded. So all of these parameters are printed by calling that set EEG reference, right? So you can see that there are 204 gradometers. I don't know what's that. Maybe someone from Ant Neuro can answer. Yep. What's FZ and what's CPZ? Why don't you come here and tell us what's FZ and CPZ? You want a volunteer? Legia is here.
Let's take this part here.
See, now we are getting more deep dive.
I'll just use a mic. So
Yeah, please.
People on Zoom can listen. So this is our EEG chart. Doesn't work. Does that work? Does this one work? No, we're all dead.
It's a very wrong day.
Works. Perfect. Okay, so let's imagine this is our EEG cap. So when you record an EEG channel, you need three things. You need an electrode. That is the electrode that you're interested in. Let's say you want to record channel, the signal coming from the back of your head. So you're gonna need the electrode that are present on the back of the caps, and that in this kind of caps, that is the classical caps used by half of the world, is called PO2 or PO3 or POZ. So these are just channel location that has been called. Yes.
Yeah, exactly.
So these are just channel location that is been decided by electrophysiologists back in the 50s. So very old stuff, not very interesting, but just so we have an idea. So these are called the electrode of interest. Then you need a ground. That is, when you measure electricity, you need something to ground to do the calculation. But then you need a reference channel. That is what you do the comparison with. to calculate the voltage between your electrode and the reference channel. The reference channel in this cap here, because our system works like that, is, and Kaylee, correct me if I'm wrong, the reference channel here is FPZ. Correct. So FPZ is a channel that is
Or what's in this diagram?
one of the central one. Yeah.
This
No,
one,
that's CZ. Is a should be this one. Yeah.
where my mouse is. Yep.
Yes, exactly. So that's our reference. Now, as Avinash showed before, no, it wasn't Avinash. It was you. Ah, sorry.
The one in white shirt.
Yeah. Hmm? Oh, yeah. Yes, sorry. So as we showed before, based on which channel you use to reference, you have different results because you do a different kind of subtraction. So usually, and there is a big debate on how you do this kind of stuff, one of the most used reference is average reference. And average reference, you just take the signal of all the channel and you do an average, and then you use that average as reference for all the other channel. And I think what the code is doing there is exactly doing that.
Is it okay to say, when I want to go to some place, I need at least some GPS locations to actually tell me where to move, where to go, and other stuff?
Let's put it like that.
Okay, yeah. I mean, at least easy for me to understand, right?
Yeah.
Right. Sorry, going back, and that's a good question I asked. Even I didn't knew that. Yeah. So, and what's this io.read raw FIF function? So that's all. IO stands for input and output. Read the raw file with this name, which is samper odd with some filter and some parameters for us to understand, right? So he's simply reading the raw file, which is specified here, with M&Es providing input and output operations. And the operation is read raw FIF. I guess there should be a function for also saving a file, right? Yeah. And what's the name? Save raw FIF, right? So you can, I think we can find it by saying mne.io.save raw FIF. Right? In the documentation, they are saying, okay, there's some IO raw. I can't find save function Legia. Okay. Where that's I'm again sidetracking. Just for saving time. So we are back here. I've read raw FIF file, and you can always look more documentation how to either read or save the data through M&E API. Yep. Next, moving on is M&E gives us a lot of data, and we are only going to pick EEG. And what's EOG, Avinash? So EOG stands for? EEG is sorry. Okay, and EOG? Electroocular graphic. Okay, that's great. So it's also sensing what my eyes are looking at. Oh, so first my eye looks at an image, Legia's image, and my brain tries to process this is Legia, not some random guy.
No, it's more it perceives movements of the eye.
Okay.
So and then remove
it. Okay. See, I'm now moving from machine learning to EEG. Yeah, I don't want to do another doctorate though.
you are in machine learning and you just jump from this EEG whole processing and just use simple metadata provided by those experts who created that data, and you just convert those data, which is much simpler to read in your machine learning. I'm not sure it's something also here in this code, but that's the idea basically. And for example, Sunny is in machine learning and he have no idea about that. And that's what expected from any machine learning person. Yeah, please continue.
Yeah, this also gives good opportunities to the scientist in the back, biological scientist, right? That there are many people who might not know what is the deep dive components in your field, but they might know machine learning. And to teach those machine learning experts how to properly process your data and honor the rituals, you can team up with some grad student or computer science student to build some libraries and then do deep learning on top of that, right? So everyone, no one is having any error in running the notebook. That's kind of the best day I had. So, I mean, that's really great. No one is having any error when you're running the demo. That's the best thing which can happen, right? Avinash, one thing, what's this MEG fonts stands for? And exclude bads, right? You can just look at the API, right? So next one is the events and the event ID. I think that's the channel.
So that's again, I want to add here. So I just show you in the my metadata thing that I choose a window from like a -0.5 to 1 second, which is a metadata and which I know because I'm aware about the data set. Here in this code also those window has been set. But if raw data is given to you, it's very difficult for you to find out what this window should be. And again, this very tiny metadata make big difference in this. What happening here, exactly what I did in the code earlier, they take this window and sample and cut the pieces from the data and create a number of different number of trials and label them target, non-target. So that's what's happening here. We don't need to go detail, but we can go forward.
Right, and once we understand that we are able to create data without even being BCI scientists, just by following M&E lab and taking some questions or suggestions from Avinash, we can obviously look at some channels, and we have a monitor of the same cap which we just saw a bit early.
This is another metadata which is always essential. So P300, like again, being in neuroscience, I know P300 happen more on the back side of the head. That's a more prominent place. And like you see, there's so many sensors, and we're looking at the sensor which is very bottom of the head. We see it's called EEG 0058. And why it has been selected? Because we know based on literature and what we learned so far that that's where P300 is supposed to be occur. If you choose any other channel, it's not. Again, this is very domain specific knowledge, and it's supposed to be a metadata information when data is available for you. You can read from paper, which is not so great. So yeah, that's what here happened. The one metadata has been assigned that this channel will gonna use when we run the processing in the machine learning.
Right. So also you can see that he's actually passing the channel he want to plot. And these functions do make sense now because plot sensors, what sensor you want to plot is EEG 058, right? And now, sorry, I can't explain these graphs. I can only run these
Let
graphs.
me bit of explain many parts.
Exactly.
Give me for a second. So again, this is again very domain specific information. Those who are in EEG stuff, they understand what we are showing here in this file. This is not essential for running machine learning code. What you have done is additional information. Just to explain what P300 is all about, which we explained from morning to several times. So I'm not sure we need to go ahead again, but to give you a very quick view, this is the window we have chosen, right? -0.5 to I think 10, 1 second. And P300 happened around something like this, which is around 400, which is not ideal, but let's assume this is P300 for this data set. And this code is
that's
just,
the epochs of Avinash, 12 epochs, which you mentioned just above. in
That's
the
right.
above cell.
that's right. So what you're seeing here is a line graph with all standard deviation in the gray and the backside averaged overall over the 12 epoch. And now this is event ID. So you remember I mentioned there's an ID called target, non-target, or 0 or 1. The same event ID. So event ID is all about label, which is stored in EEG data. But of course, when you process in machine learning, you can choose whatever name you like. So in this case, what's happening, all non-P300 data set has been chosen together, which is 1, 2, 3, 4. I don't know what's ID for P300, but they all accumulated together and created a total 208 events, or I should say 208 epochs or trials for your train the data. I'm also gonna quick go.
Run that.
Oh yeah, that's right.
Yeah, please don't forget running that.
Although again, this is nothing to do with the machine learning pipeline at all. It's just for explaining the data itself. Now, this is non-P300 cell, again, like a P300. In this one, P300 is not that prominent. You see around between 200 to 400 somewhere here, not so great compared to what you saw here, which is much more prominent, slightly prominent, or at least I say there's a difference between P300 and non-P300 data set by looking from your eyes. Of course, deep learning may extract some more information.
So in machine learning, that's what we are going to try, that those small peaks, how to figure out a small peak is non-P300 and then slightly difference is actually P300 and learn those small boundaries.
This is another example on the same thing where the both P300 and non-P300s plotted together to compare. And like you can see, the blue one have lots of peak jumping around somewhere here, which is how it's supposed to be, which is kind of P300. Again, I'm not claiming it's a P300 to be honest, but let's assume it's P300 or look like P300. Again, nothing to do with machine learning pipeline, just a domain knowledge. If we go,
and all of these plots again add a visual interpretation to a non-expert.
that's right. So from here on, what's happening, we're converting data which more machine learning readable or machine learning platform readable. So that's I'm going to hand over to Sunny. So now it's all machine learning.
Right. So just reconciling with our expert Legia here, I come back to that point. Now we have a robust scalar as a function here. Does anyone know what scaling or normalization refers to? Or everyone knows what scaling or normalization refers to? Okay, I try to give an example. In this workshop here, some of us have a doctorate. Some of us are professors. Some of us are going to be doctorate. Some of you, I don't know, maybe working in industry. So the education background, the spectrum is quite large, right? Now, if you want to specify or represent these people, how you're going to represent them, right? So because the spectrum is too big, you need some sort of reference once again that, okay, or the academic titles of each one belongs to either they are graduate, they are postgraduate, they have done their masters, so on and other stuff, right? So from raw data, putting them into such bins and bins which have bounds is normalization. That's very basic idea of normalization. Okay, so for any machine learning to work, normalization is a central player, because when we are talking about data is in digital format or floating point. So the precision is quite important. as you can see in these graphs, these subtle differences, or this orange and blue curves, are crossing each other so many times. So how can you say that a point over here actually belongs to the orange curve or the blue curve, right? So normalization comes into this picture, because now we need to say, oh, anything which is beyond 0.4 or maybe -1, either we don't care about those data points, or we want to start a reference from some point. So map that data to my reference data point. So our axis here, the time axis, is the reference data point. So we are mapping everything here. That's why we need normalization. And this is a key step which we were missing this morning when I looked at our experts code and it was not working. I think it is working now, right? So EEG data, they are using robust scalar. I don't know, this function is maybe from MNE. It's not from scikit-learn. So this function is probably from MNE software. So we are using this scaling function to scale our data. Definitely we would have used it somewhere. See, EEG data scalar dot fit transform. So this is what it is doing. It is actually normalizing our raw data and converting it to a normalization format. We can definitely look at some example. So I think this P300 is your raw data, Avinash. So why don't I say raw P300 data equal to maybe np.copy. I don't know whether this will work with NumPy, but let's try P300s and run the cell. It's just brushing the data to do machine learning, right? So converting into a format for machine learning to happen. Now we can see that we have some training data count, which is how much data points belong to one class and how many data points belong to the second class. Now let's look at some example. It actually worked. That's good. Today is a good day for me. So let's look at the raw data. Just we can put the variable name and run our cell, and it's going to print out the data. And you can see the data has negative values, or these are very, very small values. It's 10 to the power -6. We have some positive values as well, but again, it's very, very small values, 10 to the power -7 or -6. And also look at the data which is transformed or normalized. Yeah? This is the scalar function we have used. So again, so you can see now all of the data it's transformed. I still can see some negative values, but the range might be different. So maybe I can say training data dot, that's for the minimum value. Let's see whether it runs or it gives me an error. Okay, that's the minimum value for training data. And if we look at the minimum value for the raw data, hope it doesn't coincide. Yeah, so you can see the difference, right? So that's what normalization will do. It will try to spread out the data or squash it such that it becomes easier for the machine to understand the differences or learn the differences. I hope I'm giving you some insights which were not there. And you can delete any cell by using the delete icon over here. I'm sorry. Before we move forward now to TensorFlow code or the deep learning code, any question or suggestion or comment, or you want me to go through over any cell? I hope we have time, right? We have half an hour. Yep. Anything? No? I'm wearing my glasses this time. Sorry? Brain experts, they sense your movement, right? So now we are actually making a deep learning network where we are using the Keras library which is calling a sequential function. So we're going over it. It seems pretty daunting to me to understand how the layer or how the network is constructed. Do you guys understand or have made some sense out of it? Where it belongs to the same family of models, but this is just model for this demonstration, but belongs to the same family. I can make our life easier if you want. So what is happening? If you look at, I just opened Paint, which I like sometimes. So if you look at these parameters, hidden 1, hidden 2, hidden 3, and then I'm not sure we have defined this because it was output. It was output. Yeah, okay. We have defined this one. So
Yeah.
The network runs, but how to make sense is, let me open Paint. So our data is of certain dimension, right? Is 10 times, what's the dimension? Legia? Data dimension? 226, right? So Josh told you that this data goes through a sequence of layers, right? And those layers are doing some transformation, some processing, or trying to learn things. So this data goes to a layer 1, and everything is happening in sequence. That's why the name is sequential, that you're running things in a sequence. And the first layer happens to be a hidden of parameter hidden 1, and hidden 1 is of dimension 500, right? So this is going to become now from 10 times 226 dimension to dimension 500, right? And 226 is the sample count, which Avinash specified earlier. And from this 500 dimension, it's gonna become, I will call it question, that I don't care how many tries you have taken, but I'm more concerned about what's gonna become the dimension now, and it's gonna become of 1000 dimension. Legia, do you know numbers by heart? Numbers by heart. What's the next layer dimension? Okay, you're too nervous. Yep, 100, then 10, and then 1. So it's gonna become 100. And oops, I should draw it more carefully. Then it's gonna become of dimension 10, then dimension 1, right? So oh, my bad. And this is our output. Of course, there are other steps in between, but let's just understand this one, that here is our input, and here is our output. Right? So you understand first how the data is transforming among different dimensions. That's the basic mathematics. And after that, you need to understand that Legia is performing some special tricks, which is, oh, this is, I forgot, I haven't used Zoom for a long time. We can annotate. So he's using some special activation functions, such as SELU, which is it.
It's kind of special.
Right. Okay. Yeah, sorry, Ami. Yep. Yep, yeah, I can. Yep.
We should take, based on the explanations, with that there's some complex data, and the model goes through the decision between yes P300, no P300. Be a very
dimension 1. Yep.
So why is it? Oh, thanks. So why is it that from the input, instead of continuing in this reduction of dimensionality,
Yep.
you actually jump to a 500 and then 1000, where in fact
Right.
later on you want to converge to a
Right. Well,
smaller array?
that's a good question, Ami. That this configuration of network is defined by Legia, and he thinks this is good enough for this demonstration. And that's what I was saying, that once we understand the small much more network structure, the parameters, we can actually dissect it and stitch it all together. So the two things which you should understand, or which are gonna be constant, is the input, which is of dimension 10 times 2 to 6. And I'm gonna draw a box, a transformation box, right? And an output. And this is our output. Instead of saying 10 times, so this is my output, 10 times 1. This is my output. This is my input, right? And this transformation box is the key. Now you can draw a network where you feel maybe you have some different parameters, and those parameters you came up with your scientific knowledge that, oh, actually, maybe the data is too condensed. I first need to expand the data and then try to learn what happens on trying some projecting the sparse data to some higher dimension and learn from that. So all of these is actually what a machine learning scientists do to learn patterns from the data. So that's the thing. That's the idea. So in this tutorial, when you're looking at the layers, you can obviously try to remove this layer completely and see what happens to the learning and the outcome. Or you can change the dimension from 1000 to maybe 700. That's what I was explaining earlier, right? So these things you can do. He has mentioned some special functions such as activation, ReLU. It's an activation function. Basically, what it's saying, whatever is the output of after processing, sorry, what maybe the input is maybe 7.345. I'm just giving them some random numbers. After processing from the layer, it became 2.79, and this function is gonna apply on this number. So it's ReLU, which is the full form of ReLU. The proper name of ReLU, it's rectified activation function. So basically what it does is it again converts this number to some other normalization constant. But this is simply a high pass filter. So simply if the number is negative, minus 2.79 or whatever, it will change that number to 0. And if the number is positive, positive 2.79, then it's gonna pass it as such. So ReLU is simply a high pass filter. SCLU, I think these are one of the new activation functions to where they're saying, why should we throw out all the negative numbers? Some of them should be useful and how to learn from it. So I'm just gonna remove my drawings. Sigmoid is actually the activation function, which I should emphasize on that. Once the output is there, if I go back to my drawing, which is of dimension 1, how do we know this is a monkey or a non-monkey or other stuff? This is simply a number, right? So if I give you a number 5 or number 10, how can you understand? So sigmoid is simply again an activation function, which is gonna convert that number to a probabilistic output. And you know, probability is between 0 and 1. So if we are classifying between monkey and non-monkey, so probability of 0 will tend to monkey, or probability of 1, or whatever the output is, we can utilize it. I hope I'm correct. Yes, I am. Right. Sorry, I'm a funny kind sometimes. Right. This is just a demo network which we have created. You can obviously play with it and try your things. Now, I think if you recall from Josh's tutorial earlier, he said after creating network, we need to start learning of the network, right? And we need to control how fast or how slow the network should learn, right? And now for learning, many things are essential. first what kind of learning you want to inject, or what kind of function you should you allow your network to learn. And he said a name, which is gradient descent and algorithm, which is utilized to train deep learning network. Now that was one specific learning mechanism, such as if you are learning or driving for the first time, you might go to instructor one, and he has his own experience to teach you driving. If you go to another instructor, maybe he's German, he can teach you how to drive faster, maybe at 120 kilometers per hour, because they are trained to do so. And if you go to a third driver, maybe someone from India, he can teach you how to even drive in a reverse format and drive anywhere, because I'm just making fun. That's what's happening in our country, right? So Adam is one such training algorithm. So you use Adam as an optimizer to train and learn from mistakes and correct things you have done. So you have specified your optimizer, you have specified the loss. Now you're using simply mean square error as a loss because your labels are either 0 or 1. And it's simply saying how far or how near you are from your ground truth, your labels. So that's it for creating a demo deep learning network. Any problems, or someone tried a different setting, he failed, any experiment? Well, for me, it's just me talking. I even want to take a break to just sip some juice, but you guys don't have any question. Well, that's all setting up the deep learning model. And now we start training a network by using the fit function, where we are actually calling a model which we have defined earlier and the things, and we are only passing the training data and the labels and the epochs. Epochs is simply for how long you want the network to learn, right? And below is simply a graph of what happens to the network once you start training. I'm sorry. Right. So you can see over the epochs, we specified 50 epochs. So 50 runs how much the network is improving by learning. So we can say for the first 5 epochs, he was having a very high loss, which is, if you remember, or just by going back, the loss is MSE, mean square error. It was very high. So the network was not giving 0 or 1 for the whole time. He might be giving 0.7, 0.4. That's why the loss was higher. But just going through the whole data set once or twice, his loss actually became 0. So he became pretty good at giving the numbers very close to what we wanted, right? And that's what we can understand from this graph. Anything, guys? Right. Sorry, you are saying overfitting? Well, it's true that the loss has bottomed out very, very quick, but I still can't say it's overfitting, because to understand overfitting, I need to check how the network is performing on unseen data. So if I have another graph, so just annotating it, this is my loss on the training data, because that's what I am passing it. Let's say I also plot a graph over validation data, which is not seen by the network. And the graph first goes down and then it jumps. This is the case how we can say it's overfitting. Right? But we just have kept that aside from this workshop, because we don't want to pass very complicated things. If such a scenario happens, then you can say it's overfitting. But let's say you are again fitting over some validation data and your graph looks like that, that's not the case of overfitting, right? So you can see those two different patterns. One is for overfitting, another one doesn't demonstrate overfitting. So also there's one reason why it has bottomed out so quick, because in this demo we have very less amount of data which we are using to show you, because it will take time for the network to run and complete and finish its training. Also, I think I forgot one thing which I must have told you in the very beginning. Fortunately, no one asked, so I'm not punished. If you go to tools and you click your change runtime, at the moment there's no hardware accelerator, which means I'm using the browser without any GPU resources or TPU resources, which can make this deep learning run or train faster, right? So you can click and you can choose either GPU or TPU. Please don't try to do that now, otherwise it will reset your browser, not the browser, but the backend, and then you need to restart all of the steps. It's pretty easy if you want, but I won't be doing it. You're free to do so. Now let's just check how a network has, or what's the performance of a network over our test dataset. So we are using the same model, but instead of fit function here, we are using predict as a function, and we are passing the testing data. And we simply see that over 6 data points, 3 from the positive class and 3 from the negative class, he's very, very confident on all of the positive classes that they belong to category 1. And he is sometimes not so, I forgot the word. He's not so confident that these things belong to the negative class. 30% it might belong to the positive class, but that's what our network is giving, right? Obviously, with more data, it's gonna learn better. We can also plot the learning, and Avinash, I think you need to explain these graphs. Because they are going over EEG sample length and also the positive testing data. So what does these colors demonstrate? So all of these, well, simply what we can see is all of them are from the positive testing data. So these green curves representing the 3 test data points which we have used here, and the red, brown, and black curves belongs to the negative testing data point. And we are plotting over all 226 dimensions, because that was the input dimension we had. I think there is something which we might be able to see. Sorry. Yeah. So it looks very similar to positive samples. There are at least 100. Yeah, that's what they are saying, that if we plot, if we train with more amount of training data, we can see these patterns more distinctive, right? That's what the crux or the gist of this cell or this comment. Now, sorry, no need to try over. Yeah, go ahead. Yeah. Sorry. So here,
Add on.
I'm sorry. Let me take some.
So what you see so far is something where metadata doesn't exist. You see M&E is super complicated again. And well, machine learning part is pretty easy. You can have network taken from here and there and you can run it.
It's not easy.
Easy in the sense, well, okay, not easy, but it's comparatively a lot easier than M&E, given you have few layers, network, feed in the data and done with that. Now from here on, what you're seeing is the data where metadata is already available. So you completely get rid of the role of M&E. Whereas that's the title of the workshop, is how to bridge the gap between CI, which is computational intelligence, and neuroscience. And the bridge the gap is the tool which give you this data where your M&E doesn't need it at all. So from here on, that's what you do, right?
Right. So now basically what this additional part of the tutorial is, we don't have M&E now as our backend to give us processed EEG data. Rather, we are using raw data collected earlier. Am I correct? Yeah. I mean, it's all right. It's all computer science, right? So, yeah. So Avinash has given us this data collected in one of his workshops earlier, which is
In the one of you, I think, in the morning. I'm not sure who's that.
let it be anonymous.
Anonymous subject. And this data belongs to him or her.
Right. So can you download P300 data? P300 data 3. So this file you can simply download to your local drive or laptop, and you can upload this data by clicking this upload icon over here, which is the arrow pointing upwards. Click on that. Downloads. I think I need to download the data. So let me download the data. And it's taking time, but did somebody try this over this data, or you faced any errors? No. Yes, you are a bit of expert user that you got to mount the Google Drive, but without even mounting, you can do the same by just clicking this arrow button. Go to the file, confirm and upload, and it's gonna upload in the session, which I explained. The moment you terminate your session, all the data is gonna be flushed. So you did a better job putting the data on Google Drive and connecting the drive to this Colab notebook. Now there's one way to do that is simply click this drive icon, which is gonna create some set of commands for you. The moment you run it, it's gonna ask you permissions to connect to the Google Drive. If you follow, you can see that Google Drive appearing under content. And then you can find the path of the data set and utilize it. I'm not gonna do it. I don't want everyone to see what's in my drive. So I'm gonna take the lazy way, which is uploading this data on this session. And if it's got flushed out, I don't care. So sorry, what's the name? Zach, did you try any different settings other than this demo? Yeah, that's why. Try and tell us what new things you found. So it's also giving me a reminder that these files are gonna be deleted when we terminate the runtime. I think I'm gonna finish pretty soon, Avinash. Where I can at least explain until the moment data is uploading, so that I don't waste both of our time or try to speak more. So basically, we are gonna, if you remember, the first step in our M&E was to normalize the data, which they were using robust scalar. Now, in the data which we collected earlier, we are again gonna normalize the data, but for normalization, we are gonna use a package called sklearn, scikit-learn. Again, API is very well documented, and you can just go over there and go through the API. So from that API, I'm gonna import the min-max scalar, which is simply saying normalize my data between 0 and 1. Now that's good to know, but how we will be able to read the data, the actual data which I'm uploading, which is in .mat, which stands for MATLAB format, right? So that MATLAB format data can be read through another API, which is scientific computing Python library. It's module called SIO. Again, you can understand IO for input and output buffer reading and other stuff. Sorry, you want to say
just
something?
want to add here again. So MAT, this is MAT, just example again. MAT is essentially like a CSV file output from MATLAB, but you can have output of text file, Weka file, pickle, or whatever you
I
want.
think here you have opened MATLAB.
No, you don't need to show. That's okay.
Right. So basically, whatever the format is, we need to read that format. At this moment, the format is .mat. And to read that, we are using a library, which is SciPy. Again, a variable. You should have access to it the moment you start your Colab. So don't need to worry about that. Now, there's one unique thing when you read data by using this library. It reads the data as a dictionary format. Do we know dictionaries? At least the one in which we look for the meanings of particular keywords, right? So Python or any kind of programming environment provide you dictionaries where you can assign keys and then what that key will hold. So key and a value is a dictionary. So I can say, I can create a dictionary such as maybe BCI Workshop, which is a dictionary. And the first key can be participants. How many participants were there, Avinash? 30, I guess, right? Or 60, 70? 300. Oh, I don't think we have space for 300, right? So there has to be some logic. And maybe day is Wednesday. Am I correct? Yeah, it's Wednesday. I remember. It's a string. Wednesday, right? So this is just a format of defining a dictionary where participants is the key, day is again a key, and the value for each of the key is 70 or Wednesday, right? We can define it. We can print more things by saying, okay, I want to see work. Why it's not? Okay, workshop dot keys, and it's gonna print all of the keys for me. At this moment, I have participants or day as a key. I can also try to look at the value of a particular key by saying BCI Workshop. And I can say, okay, what's the value of day? And it prints Wednesday. And maybe if I say week as a key, it will give me an error, that key error, week. So simply saying there's no key with the name week, which we can verify from here, right? And now we can almost see our data is gonna be there. Just a moment, guys. Did anybody try apart from Zach? Besides Zach, did somebody try running on the data? Maybe the participants who have collected their data. No one? Oh, well, I'm happy to see you starting with deep learning. So our data is uploaded. And you can see this is the way I'm also accessing, because the moment I read this data, oh, sorry. I think I forgot to import the library. That's why it gives me an error that SIO is not defined. Now I import it and read the library. And you can see I'm reading the data, which is actual data and labels. These are the two keys in my file. And I'm also scaling it or normalizing it by using my scalar, which is min-max scalar. You can choose any scalar you want, but be careful about the physical world properties. Just again separating the positive and the negative data points, putting them into train test split, which is splitting the whole data for the model to be trained and then to test on the same network. And now we have, oh, I'm sorry, I should delete this one. That's for another data set, right? That was for another data set. And now simply running the same model. And yeah, just doing the same steps which we did earlier. So now it's taking a bit of time because we have more data this time to train this network. Let's see. I don't need to say any magic words, and we can see that the graph is not that smooth, as you pointed out earlier, Zach, that it simply went to zero, the learning or the loss. But this time it's a bumpy ride, but slowly it's going down. The trend is that it's going down over the epochs, and we can print the report, the classification report, that how does the network performs over 10 positive data points. I think no, it's okay because I ran over the second data set, so it reset that one. So sorry, yep. And now you will see again. I'm again retraining my mistake because the data got swapped with the wrong code. But you can see, yeah, from our failure, which we didn't saw, that for 10 positive data points, none of them were classified as positive, but all of the negative data points were classified as negative, right? Now you can see again, there's a bumpy ride, but it's going down. And let's see what happens now. Okay. We are doing a good job, not superb job, but for this demo, 60 or 50%, 5 data points from 10 positive data points, 5 of them are classified correct. From 40 data points, negative data points, 97% of them are classified as negative. So the network is doing a bit better in identifying the negative data points than the positive data points. And now comes the part where I said machine learning is important. Now you go in Army here and you try to make a better network who can also do a better job at classifying positive data points. So I hope the thing was not too boring and I'm able to deliver what I was supposed to. Just some extra slide that you can be a bit professional than us and try to define your network in a more systemic way or by following software engineering principles, which Dr. Avinash is teaching here. So back to you.
Thank you, Sunny. Thank you, and Sunny and Regia for nice TensorFlow demo. Of course, there's lots of bits and pieces maybe missing here and there, but I think still you might get a good idea. And like I said, so this TensorFlow demo is also a comparison between a data where you have metadata, you have this bridge with the help of the tool, which I just demo on the MATLAB very quickly, writing few lines of the code, just because I have the metadata. And the one where the metadata is missing, so you need to go through a bunch of things through the M&E and quite of knowledge, need to gain domain expertise needed to process the data. Well, from this point, we are almost toward the end of this workshop, and let me open my last slide and then we can wrap it up. So, well, again, thank you all of you are here. Some of them left. Also, thank you for them coming along. And there's plenty of people online. So thank you for them as well to joining this workshop. The agenda behind the workshop to give you a message that this connection between these two communities, this is just a one tip of the iceberg of one of the community I'm just talking about, which is neuroscience. And neuroscience is important because it can solve lots of health related issues as well, which is getting more and more complicated nowadays. So this kind of bridge is required so that the whole progress in the two community can be accelerated at very, very high rate, which is not so far. So we are almost in the end, like I said, so we have a sort of, it's not a break because you are just, it's a bye-bye actually. But what we can do, we can have some informal chat, which is usually more interesting than the workshop and seminar itself. Generally, we can talk outside. There will be again some tea and stuff should be outside by now, and we can have some discussion. I also want to thank you all of the team, which are here, is all mentioned here, myself, Dr. Sunny Verma, Dr. Harvey, all on the near the gate, Yancho, who set up lots of things, Alex is also there, created a scenario using Unity, which we use for collect data. Yanglin is also there, Ellen, in another name. So he created this website, this what picture you're seeing is all done by him, and Legia to work on that TensorFlow collab code. And then we have two experts, Josh Gordon, look at his video if you want to learn more about TensorFlow. He did quite a nice work. He have lots of nice tutorial out there. If someone want to learn about TensorFlow, I would say go for it. And Luigi Bianchi, of course, his expertise also in BCI. He's working on BCI from last 10 years, maybe. It's quite expertise, but maybe not as well known as Elon Musk, of course. And last but not least, which is not have picture because these two guys are here from A&T. Kelly just on the backside seat, if you wave the hand, and Matthew, if I'm saying right, I'm always bad in pronouncing the name for him. So again, thank you for joining today's workshop. There's a tech festival happening, if you know about it. There's lots of other events also happening in these 2 weeks. You can also go through them and join them. And again, thank you for A&T, UTS, and TensorFlow to supporting this workshop and kind of initiate this kind of discussion. Maybe at least one of you convinced, that's the goal. And thank you again for everyone.